I guess Utah is probably somewhat still less welcoming.
Yeah, it's still a little cold. Not too bad, but not Midwest cold, but definitely a little cold. Busy. It's a little bit crazy right now, but hopefully it will calm down in a few months.
Holy. So has any of the schools returned to in-person classes? Nope.
I know some schools do, but not us. I think Cornell does teach in some Midwestern school in smaller places where people are confined. Yeah. Stan Whitting, I'm told yesterday that they got all the faculty vaccinated at Binghamton. So we are still teaching online.
Us too, yes. I believe for summer, we are still teaching everything online.
So we have the lab, so not general chemistry, but the upper division lab classes that are smaller. Those are being taught in person in many, many very small sections. But everything else is all online.
Right. I think for the graduate students, at least the international students, they need the in-person class component to come to the States.
Yep.
So we are offering some smaller portion of the class as in person as well. Okay.
Hello, I mute myself.
Hi, Gojan, how are you doing?
Hey.
Great. Yeah, nice to see you.
Professor Tao.
What?
How are you?
It was great.
Great. Have you met our speakers who are here today? There's Professor Lianzhou Wang, probably you know him, and Professor Shirley Mintier from Utah. And of course, you know Yuri. Yeah. So Professor Cao is in University of Washington.
Me?
Yeah.
Yeah, I'm in Seattle. Let me see, is all other speakers here?
Only Shirley Min, she's not here yet. Yes. I think her assistant set up the schedule, maybe at a later start date for her.
So shall we start now?
Yes.
Okay.
Oh, greeting. I saw you. Are you going to kiss start? I am. Sorry, I think that's a misconnection here. So I will start. I saw you want to talk something about the journal, but I'll start. Okay, all right. So good morning, good afternoon, and good evening to all the interested scientists around the world. I appreciate you coming to this workshop from different time zones. And I am Yu Huan. I'm a professor at the University of California, Los Angeles. I'm in the Department of Material Science and Engineering, and I'm also one of the co-organizers of this international workshop. So on behalf of the editor, Professor Yadong Li, and the organizing committee, I want to welcome you all to this second part of the virtual meeting of the international workshop on nanocatalysts and green energy. So this workshop is sponsored by the Chinese Academy of Sciences and is organized by the journal Science China Materials, and it's supported by the research crowd. And I want to give a big shout out to Dr. Guilin Wang here, who's the managing editor of the journal, for putting all of the logistics together so seamlessly. And also a big thank you to Professor Guozhong Cao here for an excellent opening section yesterday. Great job. And today we are truly honored to have some of the most distinguished scientists around the world in different time zones to share their long-term contributions and recent breakthroughs in energy materials, and with one concerted goal of creating a more sustainable energy and environmental future for the Earth and also for the mankind. I guess it's more for the mankind. So for the presentations, at the end of each one, we'll have a session for questions and answers. So feel free to speak up, or you can type your questions, and I believe you'll pass them to Guilin, and I'll share those questions with our speakers. So we're sorry if we were not able to respond to all of the questions asked due to the limited time. And the last but not the least, we're really grateful to the speakers here today for their time and effort, and for their gracious support of this workshop. And we're certain that the audience will walk away fully inspired and motivated. So without further delay, let's start the second section of this workshop, in which we'll present 4 prominent speakers. And our first speaker is Professor Yuri Gogoshi. And Yuri is the director of the A.J. Drexel Nanomaterials Institute and distinguished university professor, and Charles T. Andrews and Bett Professor in Material Science and Engineering at Drexel University in the United States. He received his bachelor's and master's degree in 1984 in the Department of, in the subject metallurgy, which was material science back then, and a PhD in 1986 in physical chemistry from King Polytechnic and Polytechnic and the Doctor of Science degree from the Ukrainian Academy of Sciences in 1995. Oh, that's a lot of degrees, Yuri. Yuri is well known for his seminal breakthrough work on 2D carbide and nitride, or the MXenes, which he discovered with his students and collaborators. And this unique class of materials have quickly expanded, as we all noticed, and demonstrate their vast applications in energy, environmental protection, electronics, and medicine. And Yuri has indeed received a long list of recognitions, which for the sake of time, I'm not going to read through those. But the most recent award that Yuri received is the MRS Serbia Award. That's given to recognize his lasting and outstanding contribution to material science and engineering. So without delay, I'll pass the stage to Yuri. His topic today is electrochemistry of MXenes and their energy storage applications. Yuri.
Thank you very much, you, for this kind introduction. Let me share my screen with you. Okay, what I'm going to do today, I will try to inspire you. As you have heard, we're supposed to give you inspirational talks for younger generation here. And I will try to inspire you to explore a very large family of two-dimensional materials, carbides and nitrides of earlier transition metals, which we call MXenes. M actually stands for a transition metal. Those are these red spheres in the models. X stands for carbon or nitrogen. Those are black dots connecting the spheres in the structures. And they can also have a variety of surface terminations as a surface. So this is a very large family of materials that come in a variety of flavors and colors, that you can see. They have transition metals, so they can act as catalysts. They can change their oxidation state, those metal atoms, and store energy reversibly. And of course, they have many other properties, actually being true metals with a high density of state at the Fermi level. And this combination of properties naturally makes these materials attractive for electrochemical and electrocatalytic applications here. I'm going actually to divide
Yuri, sorry to interrupt for a second. We are looking at your presenter mode. You might want to switch a little bit.
I did something wrong. What happens to me often here. Is it better now?
This is perfect, yes.
Excellent here. My apologies. So I mixed things up. So basically, let me also switch to the laser pointer to get finally everything properly organized. So I'm going to talk first about MXenes in general, energy storage. I will talk about MXene synthesis properties, that you understand what potential applications are possible. And then I will give a couple of examples of application of MXene in energy storage here. But maybe let me start even a little bit earlier than MXenes. Let me start with two-dimensional materials in general. And you don't need to be an expert in MXenes or graphene to know that this is a very hot family materials now. Graphene is definitely leads the pack, but there are many other materials available. Some of them are old, dichalcogenides like molybdisulfide or boron nitride or clays oxide. Some of them were discovered after graphene when attention was attracted to 2D materials world. Many of them were actually made from materials which are non-van der Waals, where there are actually efforts needed to create them, not just separate the layers. And MXenes are among those. But why is so much attention to the materials here? It's a very interesting family. One reason is, first of all, that they are 2D. So you can basically build them. You put them like building blocks, one after another, to creating structures. You can combine materials with different electronic properties: semi-metallic, metallic, semiconducting, insulating. They have mechanical flexibility, optical transparency. If we think about future energy storage, wearable, transparent devices, Internet of Things, distributed, printed electronics, those are properties critically needed. You cannot take just a ceramic powder you say in current battery cathodes and process it this way. And also, by being two-dimensional, they have all their atoms pretty much on the surface. So the entire surface is exposed to environment. It's available to surface reaction, chemical, electrochemical, whether we're looking for a catalyst, electrocatalyst, or material for energy storage. There is no solid state diffusion required here. And these materials grow in numbers. There are a couple of hundreds 2D materials already made. And in 2011, MXenes entered the scene, first slowly, and then they started accelerate quickly. They're really on the rise now, with more than 30 stoichiometric compounds between these M metals and carbon and nitrogen available. A dozen of surface termination. I showed the first one here, like oxygen, OH, fluorine, chlorine, but chalcogens, halogens, other have also been shown: bromine, iodine, tellurium, sulfur, selenium on the surface. There are more than 100 stoichiometric simple structures possible. Multiply by 10 different surface termination, you get more than 1,000. Take solid solutions, you get infinite number. And particularly, if you look at this review article published about a year ago, at least as of 2018, 2019, roughly 50% of all papers published on MXenes dealt with energy applications of MXenes. Naturally, this was the first area where we started to use MXenes after discovery of this material family, and which has been explored by now pretty intensely by hundreds of research groups around the world. Let me take a step back again and discuss why we care about nanomaterials in energy storage. You hear all the time from media that we need batteries, car batteries, for example, that will charge within minutes. We talk a lot about wearable internet, Internet of Things, transparent energy storage window, and other stuff here. None of this is possible if you use conventional bulk materials. You cannot make them printable, flexible easily here. If you have solid state diffusion, you won't be able to charge battery within minutes here. And this is a review article we wrote with a couple of colleagues, Yi-Tsui, Xinliang Feng from Dresden. He actually just became a director of a Max Planck Institute in Germany. And Katya Pomerantseva and Francesca Bonacorso from Italy here, which we wrote about a year and a half ago, showing kind of this futuristic, forward-looking view of how nanomaterials can be used here. And if you work in the field of energy storage, you're certainly familiar with these plots, which we call Ragone plot. This comes from our recent paper with Patrice Simon, published last November. Think here, it shows specific power versus specific energy for different materials. And what you will see is that batteries definitely store more energy because they use redox processes, transfer of electrons. Electrochemical capacitors or double layer capacitors, supercapacitors, ultracapacitors. So those are pretty much all the names for porous, high surface area carbon, which store charge electrostatically. They can be charged very quickly. This line shows actually time scale. It can go to milliseconds, but with much less energy stored. So how can you get at that point where you can charge a battery of your electric car within 5 minutes or so? You need to store as much energy probably as earlier as in lithium-ion batteries, but you need to do it actually orders of magnitude faster to get to this point. How to achieve it? First, it's obvious we need materials where there is no solid state diffusion. So we need nanomaterials, materials with high surface area, like electrochemical capacitors, electrochemical accessible area. We need materials which will have redox like battery materials. Moreover, what does it mean charging batteries say quickly? It means that you need to run a high current through this battery. So you need materials which will have high electronic conductivity. Remember that even activated carbon used in electrochemical capacitors have conductivity in, say, tens, maybe 100 millisiemens per centimeter. Actually, very moderate. Graphene nanotubes go above, reducing graphene oxide, 2000 Siemens per centimeter. MXenes can give you 10 times more, being real metals, having high density of state at the Fermi level. So what we're trying to do in our work, we're trying to control transport of ions in electrons in electrode materials and redox reactions like surface redox of transition metals to be able to balance energy and power and move in this direction that we can have high energy, high power energy source solution here. And we are trying to use MXenes for that purpose here. And again, to remind, those are materials made of these transition metals, carbon, nitrogen, and a variety of surface terminations here. They produce from max phases, but I will not really focus much on synthesis today. A colleague of mine, Professor Michel Barzoum at Drexel, is really the father of that field. This is a large family of layered ceramics, which you can look at as transition metal carbide nitride layers bonded by layers of this A element in blue in this periodic table. But these bonds are strong, those not van der Waals bonds. So we have to etch monatomic layer out of the ceramics to break apart the structure. And then we can produce titanium 3C2 was the first one, but also many other carbides and nitrides of materials. And since they have now a transition metal on the surface and aluminum, say, or silicon or other element is etched away, transition metal won't remain unterminated. If you use etching in aqueous media, we will get oxygen, OH, or fluorine, HCl, chlorine from the acid. If you use molten salt, you can get other surface termination like halogens here. But the idea is we get structures with those surface terminations. Moreover, we can make not only pure structures, we can make atomic sandwiches where one element like moly is on the surface, another element like, for example, titanium is squeezed in this sandwich in the middle. It's also possible to make structure with alternating atomic columns of different transition metal, for example, moly and yttrium or scandium. And if you remove yttrium or scandium, you end up with ordered divacancy MXenes, structures where monatomic columns of one element are missing. So you get the idea. We can really do atomistic engineering at the best level. And to take it further, we can mix different atoms in solid solutions in both actually X layer carbon nitride, but also in M layer. For example, you can imagine catalytic material with, say, moly or tungsten atom surrounded by titanium atom, a kind of single atom catalyst. So, and you can pretty much create an infinite number of compositions. But the research goes on. About a year ago, we published this paper in ACS Nano, showing that we can make materials with actually 5 layers of transition metal bonded by 4 layers of carbon, moly for vanadium, C4, thicker structure. And transition metal inner layers gives electronic properties, electronic conductivity. Free electrons of transition metal provide for this conductivity. And the outer layer, terminated by oxygen or OH, gives this reversible redox. So we basically have a material which is conducting like metal. And keep in mind, graphene even is a zero band gap semiconductor, but those materials have high density of state at the Fermi level. And at the same time, its surface looks like a surface oxide or hydroxide. So you can run the same, say, electrochemical reaction like with oxides. And they can have conductivity like a 3 orders of magnitude higher than activated carbon using supercapacitor, or at least an order of magnitude higher than, say, reduced graphene oxide. It's very important, again, for high power applications. But these oxide-like surfaces give also easy processability from aqueous solutions, and they are electrochemically active. Otherwise, these flakes look like flake of many other 2D materials. You see, for example, a hexagonal imprint of the structure. Those are single crystal. This is a single layer, single crystal titanium 3C2. This flake is about 20 micrometer in length. And you can pack thousands of those flakes in this type of structure similar to, say, graphene or graphene oxide paper. And it's all possible. There's also one more important feature of those materials. There are more than 200 two-dimensional materials which have been reported. Only a handful of those can be made in any significant amounts. Graphene, moly disulfide, boron nitride, some oxides here. MXenes are produced by wet chemical etching from ceramic precursors, MAX phases. This is a reactor which was designed by Materials Research Center in Ukraine for us. We have a couple of reactors of different volumes. We can make up to 100 grams per batch. In industry, there are reactors already capable of making kilogram per batch. Fundamentally, it should be possible to make a ton of material per single run in a reactor. And what you can see here, it's about 50 grams of titanium carbide MXene, this powder, produced from this ceramic precursor. And you can take this material, basically we etch, we delaminate material, we wash it, we filter material, we get powder. Or we can simply dissolve it in water. This is a 1 liter bottle of solution of MXene. It's dark, probably about 10 milligram per milliliter. We have a 20 liter, like a 5-gallon tank standing, filled with this solution in the lab here. And what is also nice, you can process it from aqueous slurry. MXenes have oxide or oxygen or H group on the surface, so they are hydrophilic and negatively charged. You can concentrate, make, for example, liquid crystalline solution and use Dr. Bley method to produce this film. It's just 1 micron thick and it has strength higher than aluminum foil and about 15,000 Siemens per centimeter. No additive, no nothing. You just spread the solution by Dr. Blade, dry it, and you get this film. Considered to be electrode current collector. And I will talk at the end of my talk a little bit about MXene current collectors that actually suppress growth of lithium, potassium, sodium dendrites here. But you can also use any other processing method. You can print them, inkjet print, 3D print, draw with MXene, spin coat, spray coat, pretty much anything you can do with aqueous colloidal solution, including making this type of films by simple processing. And again, I'm stressing this because, say, if you take a graphene oxide, you can process it from water, but then you need anneal it. You need to reduce it to produce reducing graphene oxide, which is conducting because RGO, conductive GO is not. Here, you don't need anything. You take many other materials. You need to add surfactants to carbon nanotubes or graphene to be able to disperse them in water. No additives needed, no binder, no additives, no nothing. Moreover, you can use MXene as a binder. And all this justifies and motivates electrochemical applications of materials in energy storage. So why are they attractive? First, as I mentioned, they are highly conducting. They're actually probably the most conducting of materials used in energy storage today, at least titanium carbide MXene. But their surface looks like transition metal, oxide, hydroxide, fluoride. It's actually oxygen-terminated surface predicted by DFT to be the best one for a variety of energy storage applications here. And these layers of transition metal with electrons available for conductance make it through metals allow fast transport of electrons, and galleries between the layers allow for transport of ions. I'm going to give a couple of examples first on aqueous systems. We start with intercalation water just after synthesis, and we have protons there. But there are, of course, possibility to use organic electrolytes, ionic liquid electrolytes, work with lithium, sodium, potassium, and other elements. And what we do in my lab, we first do electrochemical characterization, cyclic voltammetry, galvanostatic charge-discharge, impedance, electrochemical impedance spectroscopy. And then we look in situ, studying the mechanisms of processes to understand what is going on when ions go in MXene. Are there redox reaction? Is there charge transfer? And with this, we can basically understand what is going on with the material and learn how to control it. Because keep in mind, we have dozens of simple compositions. We have variety of surface terminations. We have many more compositions that are possible and solid solutions. So our challenge is to select which one is the best, how to control the surface termination, how to design architecture. We can make freestanding films. Actually, MXene don't need current collectors because of this conductivity for testing. But we can also use multi-layer powder and prepare electrodes in a conventional way using, for example, polymer binders or just slurries on a current collector. Both are possible. And also in aqueous system, we use as counter electrode, usually activated carbon and reference electrode and 3-electrode cell, experiments from which I'm going to show it to you now. And what we find there, if we take some of the salts, for example, sodium sulfate, we get cyclic voltammograms, which is perfectly rectangular, very much resembles that of double layer capacitor carbon. So we assume probably no redox. But in a protic electrolyte, you will see these peaks, which are electrochemically reversible, but shift slightly and separation increases as we increase the rate here, getting high volumetric capacitors. So first message is different ions give you different processes here. Moreover, if you look more carefully and take thin film electrodes and charge and discharge it in sulfuric acid solution, it's very interesting. We get a double layer envelope and we get this broad reversible peak. Moreover, up to rates of maybe like 5 volts per second. It's electrochemically reversible. So separation is like less than 20 millivolt between the peaks here. So we get a redox, and I don't have much time to talk about it, but it's basically we switch between oxygen and OH as we go in voltage down to -1 volt, and we pretty much transfer an electrons to oxygen terminated titanium atom by doing this. As a result, we can get very good capacitance values in spite thicker and heavier materials than carbon. And if you look volumetrically, we can go to about like a 1500 farad per cubic centimeter because again, high density of MXenes here. But if we take different ions, we can observe very different behavior. For example, some ions like aluminum or magnesium, lithium will bring water in when they intercalate between MXene layers. Some other ions, like tetraethylammonium, will push water out. Some ions will hardly change interlayer spacing when they go between MXene sheets. And understanding and appreciation of these factors is important because ions that go inside even with water but come close to the surface of MXene, they are able to polarize surface of titanium or other, again, it can be moly, vanadium, niobium, other transition metals. I'm just giving an example of the most common MXene here, and definitely lead to more significant charge transfer. As a result, larger capacitance values. It's an inverse of a distance of cation to oxygen of the surface in this case here. So it means that if you even take different ions in aqueous solution, you can get different results. Same things happen in organic electrolyte. This is now lithium TFSI in DMSO, acetonitrile, and propylene carbonate. And what we found when we studied this system, the results were very anti-intuitive. Highly conducting acetonitrile solutions that in a supercapacitor, conventional supercapacitor, carbon supercapacitor, should give the highest performance, actually got the lowest capacitance area under cyclical thermogram. And propylene carbonate with an order of magnitude lower conductivity gave us a much larger cyclical thermogram. So what is going on? What we found is that in case of DMSO acetonitrile, lithium ions go between the layers with solvent. DMSO at least have them both on the surface adsorbed and mixed inside, so there is a fast transport. In case of acetonitrile, lithium ions go to the surface of MXene, but solvent molecules separate layers, hurting electronic transport and also taking space and also leading to like a brazing of the electrode expansion contraction. But in case of PC, there is a complete desolvation and lithium ions go between the layers without solvent, giving more energy stored, larger charge storage, but also no change in the spacing as we cycle the electrodes. It's totally stable here. So a message from this is that whenever we take new materials, it's not easy to introduce them in energy storage system. We need to understand the effect of ions and solvents on the behavior of this new material system and select them appropriately to achieve the performance. What is also important, you can use MXenes as active materials in supercapacitors, batteries, and in also hybrid devices. But a lot of improvement can be achieved by also using them as passive materials or both passive and active material, using them as current collectors, using them in a binder, for example, for silicon, tin, or other materials with large volume expansion, poor conductivity, but high capacity, large energy storage ability. And you can use them actually instead of polymer, even for activated carbon in electrochemical capacitor to accelerate and improve charge storage here. And of course, this application start finding use in many different systems, for example, in lithium and sodium sulfur batteries, where MXenes can be used as host for sulfur. They strongly adsorb polysulfides. Linda Nazar was the first one to show this behavior, and many other groups, including our group, followed up. They can adsorb polysulfide, they can catalyze transformation. They can also be used as films and separator to prevent polysulfide transport to anode, and also as support for lithium or sodium growth on an anode, replacing copper or aluminum here. And you can see, for example, stable cycling of a battery. This is not our work from the published result with MaxSyn electrodes and very good Coulombic efficiency over about 800 cycles and moderate loss of capacity here. But what is also important, whenever we have new materials, we need to think where they can make real impact and difference. And if we talk about two-dimensional materials, nanomaterials, naturally those are flexible devices, printable devices on a chip, or wearable devices here. This is where you need to consider those materials here. And if you talk about this type of a transparent, for example, conducting films to replace ITO, uses current collector or battery electrode, you also can think about extra benefits. For example, suppression of lithium dendrite. And this is a paper with Professor Yinjin Wei and Alex Gao from Jilin University, showing stable cycling over actually 100, 600 cycle here of lithium and uniform film of lithium because of planar growth of lithium, not dendritic growth on the surface of MaxSyn here. So there are many other applications which I simply cannot cover in this short talk. What I want to give you just a flavor of the field. This very large family of highly conducting materials with redox active surfaces, with a variety of transition metal on the surface, with several different structures, with a different number of layers and different arrangements of atoms there. And of course, they already are being explored in many different electrochemical applications here. From electrochemical capacitors, lithium, sodium-ion capacitor, to pretty much all kinds of batteries, and so on and so forth here. To electrodes, brain electrodes, implantable devices, electrochromics, and electrocatalysis. There are many, many other applications, but I have just a couple of minutes left, so I need to wrap up before my time is up here. If you want to learn more about electrochemical application of MaxSyn, this review article in Nature Materials is a good starting point, but keep in mind, it is getting dated. There are several other reviews from other groups published more recently. And of course, there are many applications beyond energy storage I mentioned today. There are applications in electrocatalysis. For example, Moly2C is an excellent hydrogen evolution reaction catalyst. You can also do photoelectrochemical catalysis because MaxSyns are plasmonic materials. You could see these different colors for different MaxSyns in the beginning. About 50% of all publications today deal with a single material, titanium 3C2 MaxSyn. TX stands actually for surface termination. Sorry, I didn't explain it from the beginning, and I used it in many slides here. It's a great material because it's made of earth-abundant elements. Titanium, carbon among the most common elements used, non-toxic, biocompatible. That's why implantable electrodes and like a photothermal therapy or dialysis are possible with this. But for electrochemical applications, moly, niobium, vanadium may be able to transfer more electrons, do better redox. Definitely, they are better catalysts for majority of reactions here. So there is a lot to explore here. And of course, we do this exploration not alone. This is my very international, great research group. Those are people who have done research I showed to you today. This is actually a picture taken more than a year ago, before pandemic, at my flat. We collaborate with many people at Jackson University in the United States and around the world. This is just very, very small subset of collaborators here. Also, much of our electrochemical energy storage research has been supported by the Department of Energy, by FIRST Energy Frontier Research Center, where we work with colleagues from Oak Ridge National Lab and a bunch of universities on MaxSyns here. And with this, I am going to stop. I think I just have 2 minutes left for questions. Thank you very much for your attention. I will be glad to answer questions, if any.
Thank you very much, Yuri. It's just a fascinating talk to hear about the genesis and growth of vaccines. So this workshop is being broadcasted over multiple platforms, reaching over 5,000 audience right now. But we're going to open the floor up for questions. For those who are here, feel free to unmute yourself and ask questions. And as I receive the questions from the other platform, I will pass them on. Anybody? So I do have a kind of more general question, Yuri. It seems everything is ready, right? You have these excellent properties. I'm talking about energy storage. It seems the synthesis have been scaled up. What do you think will be the next roadblock to bring vaccine into the real applications or devices?
Well, there are many. We always need to be realistic. There is a long way from initial discovery and demonstration of feasibility to practical real-life applications. Kilogram quantity seems to be a lot, but how many kilograms do we need for a Tesla car battery? So we anticipate that initial application will be in small scale, small size devices, in catalysis, in flexible electronics, and so on. We definitely need to learn much, much better how to deal with these materials. And we have overcome a couple of, for example, major obstacles, how to scale it up, and second, how to improve stability. We currently can keep slurry of two-dimensional flakes solved in water at room temperature. In case of titanium 332 MaxSyn, up to a year. For MaxSyn, that are considered to be the least stable, like V2C, for a month, at least. And in a film, they can be basically used for a long time. Even in sulfuric acid, you can cycle it for a year and basically take a device which has been stored and recycle it. But there are many more applications. We don't still understand exactly the mechanism of intercalation of many ions here. We learn how to truly get multivalent ions between the layers for the batteries. And we're trying to find where is this sweet spot for applications here. Where will be the first application? And actually, currently, electronic application, communication, antennas, electromagnetic shielding seems to be the entry point maybe for MaxSyn. Biomedical, medical electrodes, when MaxSyn simply replace gold or platinum, performing better than those here. And then we need to grow the volume because it's again economy of scale to decrease prices here. So I think there is a long way to go, but there is plenty of room for discovery because there are so many materials, and it's a blessing and a challenge. I did not talk today about modeling simulation at all, but tremendous amount of work has been done. Much more is needed. We really need guidance from artificial intelligence, which materials to create, how to optimize it for different type of ions, different type of electrolytes in the batteries here. So I think we just like opened this area for research and applications. And now it's up to research community to enter and benefit from this wealth of 2D materials available to them.
That's great. I agree. This is indeed a very versatile and fascinating material platform. Thank you again, Yuri.
It's my pleasure.
For one, and for a question.
Yes.
Yeah, Yuri, it is you have the two-dimensional materials, and my understanding, the edge will be the most active reaction site. How do you control those edge? And another question is, for example, like the application you have for battery supercapacitors, you want the layer to grow vertically, not in this way. Mm-hmm. Is there any thought?
Well, basically, you are right about many of these things, but there are a couple of things here. One, for example, in electrocatalysis, it has been shown in HR that unlike dichalcogenides, actually the entire surface is electrochemically active. However, edge is edge is a challenge. This is actually where oxidation in water or in air starts. So what we worked on to develop process that basically keeps edges straight, which keeps material stoichiometric. There are fewer points where degradation starts here. So control is important, very important here. Second, I really did not talk at all about architecture design today. We make this material as really like a flakes powder, but 2 years ago, we published a paper in Nature with Professor Shu Yang from UPenn, from Material Science and Engineering Department, showing that by using this liquid crystalline approach, we can make a film in which flakes are pretty much vertically oriented. And as a result, we got up to 200 micron like a thickness independence capacitance here. So yes, electrode architecture design is again another important task when you deal with 2D materials. One good thing is here, people have done a lot of work on graphene and other 2D materials by now. And if you're entering the field of MXene, you don't need to reinvent the wheel. It's very helpful to build on existing knowledge for other 2D materials on processing and actually apply it to MXenes here. But all these issues are valid and important.
Great, thank you. So for the sake of time, we'll move on to our second speaker. Thanks again, Yuri.
Again, thanks everyone and goodbye. Let me stop sharing my screen and go silent.
Right, so now let's welcome our second speaker for this session is Professor Shirley Ming Tier. Professor Shirley Ming Tier is the Dale and Susan Potler Endowed Chair in Biological Chemistry and also the Associate Chair for Diversity and Inclusion in the Chemistry Department at University of Utah in the United States. And Shirley received her PhD in chemistry at the University of Iowa in 2000 before moving on to a faculty position at St. Louis University. She stayed there until she moved to University of Utah in the year of 2011. And her research interest focused on a wide variety of areas of electrocatalysis, including fuel cells, electrofuels, electrosynthesis, and sensors. Professor Ming Tier's work has been widely recognized. She's the recipient of multiple national and international awards. Without exhausting them, there are Scientific American Top 50 Award, Society of Electroanalytical Chemists Young Investigator Award, Electrochemistry Prize of the International Society of Electrochemistry, and also the Charles N. Rady Award from the Society of Electroanalytical Chemistry. And she's also the fellow of AAAS. She's the elective fellow for both the International Society of Electrochemistry and Electrochemistry Society. And without further delay, I will pass the stage on to Professor Shirley Ming Tier. She'll talk about bioelectrocatalysis. Shirley.
Thank you so much. Thank you for the kind invitation. And are my slides, are they in the correct form?
They're great.
Perfect, okay. So I'm going to tell you a little bit about what my group has been doing, kind of more on the biomaterials side of things. And so to give you a little bit of background, I actually did my PhD work in traditional hydrogen oxygen fuel cells and kind of developing electrocatalysts that would sort of minimize the use of platinum and platinum group metals. So I have a background in electrocatalysis, and for, I guess, about the last 20 years, we've been using that background to transition from traditional electrocatalysis to bioelectrocatalysis in fuel cells. And really, if you think about the difference between a fuel cell and a biofuel cell, the only difference is that you're exchanging what is typically a metal-based metal nanomaterial catalyst at the anode and or the cathode with a catalyst of biological origin. And you might say, why would I be interested in using a catalyst of biological origin? And the real reason is really just to open yourself up to a much wider variety of fuels. So if you think about a fuel cell and you compare it to a living organism, the sort of fuel is basically everything that we eat. So we consider it food. In the fuel cell world, we consider it a fuel. And so if you think about it, hopefully, whether you're having breakfast, lunch, or dinner right now, hopefully you had an opportunity to have a little bit of carbs, a little bit of protein, a little bit of oils, a little bit of fat and protein. And you have the metabolic pathways within you to break those down. So biocatalysts in comparison to, say, platinum catalysts are really good at deeply oxidizing really complex fuels. And so that's actually how I got interested in biological fuel cells, because pretty much anything you can think about yourself or a microorganism metabolizing, you can think about using as a fuel. So this allows you to continue to think about a lot of the alcohol-based fuels that, that we talk about with fuel cells, but it also opens you up to, thinking about carbohydrates, thinking about oils. We've, made fuel cells that will oxidize JP8, so jet fuel, because essentially there are microorganisms that are used to clean up waste spills, so oil spills. And we can use those metabolic pathways and those microorganisms to actually oxidize, really complex fuels. So that's kind of the good part of biofuel cells. The bad part of biofuel cells is that when you think about a traditional catalyst, if you think about a small platinum nanoparticle, it's a small platinum nanoparticle. It has many active sites. So it could be, on the order of, say, 2 to 5 nanometers. So similar size to the proteins that I'm going to talk about today, but it has many active sites. And the particle itself is conductive. So it can conduct electrons to and from your current collector very easily. If we think about those proteins that are responsible for metabolism, they are not conductive. So you have an active site, a single active site for every kind of 5 nanometer particle. You've got one active site, and that one active site is sort of buried in a protein or peptide structure that is not conductive. And so that means that really the challenge in biofuel cells is being able to get the electrons in and out. And there's really 2 main strategies to do that. The first strategy is direct electron transfer. Can I orientate that protein so that my active site is within tunneling distance? So can I get my active site to be within a nanometer of the electrode surface to be able to tunnel electrons effectively? And this is quite a bit of a challenge. There are certain proteins that are typically small and can easily do direct electron transfers, but a lot of proteins can't do direct electron transfer, and we have to instead sort of have mediation schemes to be able to mediate those electrons to from the electrode surface. And that's really what my group does a lot of, is the sort of materials electrochemistry to design materials to help biological entities interface with electrode surfaces. So we design things like redox polymers that can do self-exchange-based conduction of electrons to the electrode surface. We functionalize or design nanomaterials that can orientate proteins so that they can do direct electron transfer. We make all kinds of sort of mimics of cellular membranes to be able to keep membrane proteins happy at the electrode surface. And we do this for a wide variety of different applications. So some of those are in biosensors, and that's probably the largest application of bioelectrochemistry out there. So all the glucose test strips that people use who are testing their blood glucose, diabetic patients testing their blood glucose, all of those are sort of bioelectrocatalytic systems. So we do a bit of biosensor work. We do a bit of work on energy conversion. And more recently, we're doing quite a bit of work in electrosynthesis. What I'm going to talk to you today is sort of the energy side of things, and really kind of how you can take these biological nanocatalysts and actually get them to function on electrode surfaces for energy conversion devices. And so if you think about this, most of the metabolism in a living organism, those metabolic pathways are basically based on a, hold on, let me get my pointer to work here, sorry. are based on NAD-dependent dehydrogenase enzymes. So most of the oxidation that happens in metabolic pathways actually require a cofactor NAD that actually binds with the substrate or the fuel that's being oxidized. And when you oxidize the fuel to its sort of first product, you take that cofactor NAD and you form NADH. And so really then you're using that NADH as a mediator to mediate those electrons and sort of regenerate that cofactor NAD. And so if you look into the literature, people have been basically developing electrodes that are NAD or NADH based for about 40 years at this point. Myself, only about 20 years, but historically, people have studied a lot of these NADH systems. And the thing that they're challenged by is the fact that if you look at NADH electrochemistry on most inexpensive current collectors, so things like carbon paper and carbon cloth, you have overpotentials for NADH or NADH oxidation that range from 500 millivolts to a volt. So if you think about a fuel cell as a 1.2 volt battery for all intents and purposes, if you lose a volt of that to the overpotential of NADH oxidation, then okay, yes, you have a mediation scheme, but you're not going to have a very useful battery. And so we have to add an additional electrocatalyst here to actually catalyze that NADH oxidation to regenerate the NAD. Methylene green, which is a phenothiazine that has actually been discussed for redox flow batteries, is also a well-known electrocatalyst for NADH, and it's very easy for us to electropolymerize it directly on an electrode surface. So we can take a carbon paper or carbon cloth electrode, place it in a solution of methylene green in a borate buffer, and as we scan, I will tell you that I'm from the electroanalytical community in the US, so this notation is polarigraphic notation and not IUPAC notation, so I apologize if you might have to look at it upside down and backwards. But as you start scanning in the positive direction in that solution of methylene green, you'll absorb a first layer of methylene green, and then at potentials past 0.8 volts, you'll polymerize it. Then you can scan back, deposit another layer, polymerize it. Scan back, deposit another layer, and polymerize it. So you can do a layer by layer deposition of this conducting polymer that will act as an electrocatalyst for that NADH oxidation. So if you think about it, we're basically taking carbon cloth or carbon paper, we're coating it with an electrocatalyst, and then we're coating it with one or more enzymes. And that's really what I wanted to talk to you about, is sort of the enzymes and the placement of the enzymes on the electrode structure to actually allow us to have efficient bioelectric catalysis. So as I said, hopefully all of you have had breakfast, lunch, or dinner, depending on what time zone you're in. And so you within yourself have a series of metabolic pathways that are breaking down and completely oxidizing whatever it is that you consume. So if you're consuming sugar and that sugar is going to be oxidized by the glycolytic pathway into something like pyruvate, and pyruvate will feed into the Krebs cycle that is in your mitochondria to completely oxidize that pyruvate to CO2. So metabolic pathways are excellent and very efficient at deeply and completely oxidizing a wide variety of fuels. You don't have to just have carbs. We actually don't want you to just eat carbs. You can have a completely balanced meal. And as you eat a completely balanced meal, you have metabolic pathways to break those down. And so, early on when we got interested in biofuel cells, we were interested in whether or not we could actually get these metabolic pathways to function on electrode surfaces so that we could actually use them for energy harvesting. And so you might think I'm going to talk about glucose or sort of sugar fuel cells, but I'm actually going to start with pyruvate fuel cells, mainly because the glycolytic pathway is electrochemically boring. So if there are any biochemists in the audience, it's biochemically beautiful, but it only has one oxidoreductase or one electron producing enzyme. So it's electrochemically boring, whereas the Krebs cycle has 5 oxidoreductase or 5 electron producing enzymes, and is therefore sort of much more interesting from that perspective. And so we wanted to see, okay, can we take a metabolic pathway and get it to function on an electrode surface and show that we can use enzymes to deeply oxidize really complex fuels. And so what we did was take the Krebs cycle or the citric acid cycle and look at it in terms of what was out there in the literature. And so pyruvate is the main substrate for the citric acid cycle. And there was actually research in the literature where people had taken pyruvate dehydrogenase, immobilized it on the electrode surface, and shown that you could get 2 electron oxidation of pyruvate. You also can get 2 electron oxidation of pyruvate on some platinum alloys. So that's not particularly impressive all on its own. So what we wanted to see is, could we add both electron producing enzymes, the enzymes here in red, as well as the non-electron producing enzymes of the Krebs cycle to actually get this full pathway to function and completely oxidize pyruvate to CO2. So we decided to sort of make electrodes where as we made additional electrodes, we were titrating in additional enzymes to more deeply oxidize our pyruvate fuel. And so our fuel cell looks a lot like a traditional hydrogen oxygen fuel cell. So you basically have that MEA structure where you have a separator here, Nafion separator. Our cathode is an air-breathing sort of platinum cathode, but now on our anode we have carbon paper. That carbon paper is coated with our electrocatalyst to regenerate the cofactor, and it's coated with one or more of the enzymes of the Krebs cycle, where we start with just a single dehydrogenase, then we add a second dehydrogenase and its corresponding non-dehydrogenase until we have the whole pathway functioning. So we basically made 5 different fuel cells here, or 5 different anodes at least. They all have the same sort of separator and cathode, but 5 different anodes where we had 1 dehydrogenase, 2, 3, 4, and 5 to try to completely oxidize that pyruvate. And when we do that and we look at the power curves, it's quite interesting because we're titrating the same catalytic activity of the next enzyme down onto the electrode surface. And so you'd expect as we go from 2 electrons to 4 electrons, we would double our current, and since power is current times voltage, we would sort of double our power. So we would see these sort of doubling, tripling, quadrupling of our power curves. And when you look at the power curves, you can see down here in pink when we just are doing that 2 electron oxidation of pyruvate. When we go from pink to blue, we see an increase in current. Then from blue to yellow, another increase, but we're not quite doubling and tripling until we add this final enzyme, malate dehydrogenase, to the system. And we see this huge 26-fold increase in current density and power density. And this is a perfect example of doing research and expecting to see things double, triple, quadruple, etc. And then you suddenly see this 26-fold increase and you're like, something must be wrong. We have to go back to the drawing board. And in actual case, nothing was wrong with the experiment that we were doing. It was just naive of us as electrochemists to not really fully understand the biological system. So unlike a chemical system, biological systems have built-in metabolic control. And that built-in metabolic control means if you build up any one of these intermediates, that intermediate will actually inhibit previous enzymes of the cycle. So in order to keep metabolism from going awry and keep life functioning, the metabolic systems have this built-in metabolic control where all of the intermediates actually inhibit other enzymes of the pathway in order to maintain that control. And so if we start to make an artificial pathway that doesn't have the whole cycle, we start to build up intermediates, and those intermediates actually affect this initial enzyme, pyruvate dehydrogenase. And so it's not till we add the final enzyme and we actually have this cycle functioning, then we aren't building up intermediates and we see higher current densities and higher power densities. We've applied this concept to other metabolic pathways or even other substrates, like for instance, adding additional enzyme lactate dehydrogenase to oxidize lactate. And we see much the same system. If we have a natural metabolic system, it has built-in metabolic control. And we see that over and over and over again. Some things to think about when you're thinking about biofuel cells is that we oftentimes talk about energy density or specific energy. And in the case of a biological fuel cell, it's not just the energy density of the fuel. It's not just how many electrons you can get out of the fuel, but it's also the solubility of the fuel because these have to operate in an aqueous environment. So if we look at the two examples I just showed you, pyruvate and lactate, pyruvate's not very soluble. It's only soluble to about 1 molar. And so if you look at theoretical energy densities, even if you do complete oxidation, they're still pretty low. Where if you look at lactate, lactate's extremely soluble and you can get really high energy densities from completely oxidizing it. So the moral of the story is you need complete oxidation, but you also need to have high solubility to be able to make energy conversion devices that are ideal. Now, I told you that the Krebs cycle or the citric acid cycle exists in the mitochondria. And I'm an analytical chemist, an electroanalytical chemist, but an analytical chemist by training. And that means we spend a lot of time thinking about what would be good control experiments and what are good blank experiments. And really sort of thinking about experimental design. And so as we started to take all of these purified enzymes and make these electrodes, we started wondering if we couldn't use mitochondria as a control experiment. So in theory, mitochondria has evolved to have all of the enzymes of the Krebs cycle and all of the enzymes at the right concentration to have high flux through the pathway. So it efficiently takes pyruvate and completely oxidizes it to CO2. So we were like, can we actually just lyse the mitochondria? They have all the enzymes in the right concentrations and use that as an experiment. And so we actually made sort of mitochondrial fuel cells. And we basically made two different types of mitochondrial fuel cells, one with lysed mitochondria, one without lysed mitochondria, so intact mitochondria. And if you think about this from electrochemistry perspective, anytime you have to a resistance to transport, like the transport of pyruvate over a mitochondrial membrane or across a mitochondrial membrane, you would expect to see kind of decreases in current density associated with that sort of resistance to mass transport. So we actually expected to see sort of very little response for the intact mitochondria because of that resistance to transport of the fuel across the membrane, but seeing sort of really ideal response associated with the lysed mitochondria because we didn't have that resistance to transport, and we also had all of the enzymes kind of in their right concentration to be able to have high flux. But that's not what we saw electrochemically at all. So we actually saw the opposite of that, where the lysed mitochondria had a very small response. The whole mitochondria had a really large response. And at this point, you again go back as an electrochemist and say, okay, you know, biology is confusing. When you sort of go back to that biology, you have to think here, there's something special about whole mitochondria. And that's something special about whole mitochondria when you go into the literature is the fact that Paul Schreier at the University of Texas had proposed back in the late 80s and early 90s that in order to have the fluxes through metabolic pathways that we have, and remember from an electrochemistry perspective, flux is our current density, in order to have those sort of high fluxes through metabolic pathways, you couldn't have the individual enzymes by themselves. They had to form super complexes. And he proposed that these super complexes existed and that they actually formed channels between active site 1 and active site 2 and active site 3. So not only are you putting active sites close together so that you have sort of very small distances to diffuse across or to transport across, but also you had little tunnels that were allowing you to ensure that your intermediate was going from enzyme 1 to enzyme 2 and not finding enzyme 4, 5, 6, 7 by mistake. And so he proposed this, that we didn't really have the structural biology techniques at the time to be able to prove that this was indeed in a structure. So when we got interested in this, we had to decide to go into a little bit of, do a little bit of structural biology ourselves. And we actually took his sort of proposed structure, which is the dark system here, the dark figure. And we went back and actually used current structural biology techniques, so cross-linking mass spec techniques to actually find out that he was indeed correct. There was a metabolome. There are tunnels that go between active site 1 and active site 2, but there are electrostatic patches, and since our intermediates are all negatively charged, these positively charged electrostatic patches actually keep the intermediates from going from one active site to the next active site to the next active site. So we want to see if this could actually be useful to us electrochemically. So we actually took Saccharomyces, we took yeast, we isolated their mitochondria, so little orange dots here are the mitochondria. We treated the mitochondria with homobifunctional crosslinkers to crosslink that metabolome in place. We lysed the mitochondria, isolated the metabolomes, put on electrode surfaces, and actually showed that we do see much increased current densities and power densities associated with having the metabolome. So the metabolome is important, and biology makes this metabolome all on its own. We needed to figure out how we could make the metabolome sort of outside of this system. So we were interested in kind of combining biomaterials and nanomaterials to see if we could artificially form a metabolome. And so we use a lot of carbon nanotubes for our electrode structures. So we took carbon nanotubes and they're sort of single-stranded DNA that will wrap itself around carbon nanotubes. And then we actually could hybridize a second portion of that DNA and actually have regions of the DNA that will actually bind zinc finger domains on proteins. So we took two enzymes, alcohol dehydrogenase and aldehyde dehydrogenase, that are responsible for oxidizing alcohols to aldehydes and then aldehydes to either acetate or formate, depending on whether you started with ethanol or methanol. And with the help of Scott Banta at Columbia University, he functionalized these proteins with zinc finger domains that would actually bind specific double-stranded DNA regions. And we could change our spacers, so we could change how close or how far the proteins were apart. But the hope was that we'd be able to design an artificial metabolome that would form directly on the electrode surface. So what we did was basically take the carbon nanotubes, a really long strand of DNA, only part of which will be hybridized, sonicate them together so that the DNA winds around the carbon nanotube, hybridize with that second short tier that has sort of two binding components and a spacer, cast that on our electrode surface, place that in a solution that contains the proteins with the zinc fingers on them, and it should self-assemble into a structure. We then have to make sure that it can still do catalysis, and we did indeed show that it can still do catalysis. And when we get done, we can actually see that when we have that DNA forming that metabolome, we have significant higher currents than if we don't have the DNA. So indeed, the performance is enhanced by us being able to sort of develop this metabolome on the electrode surface without having biology do it for us. Now, these are everything I've shown you to date has been all natural metabolic pathways. And one of the things that we're really interested in is designing non-natural enzyme pathways. So if you think about a fuel like glycerol, glycerol is pretty high in energy density. It's a byproduct of biodiesel production here in the US, which makes it pretty inexpensive. It's low in volatility, but if we were to oxidize it through its natural metabolic pathway, it feeds into the side of the glycolytic pathway and through the Krebs cycle, and 21 enzymes later, you can completely oxidize glycerol. I have some really fantastic graduate students, but none of them wants to figure out how to find a way to get 21 enzymes to be functional on an electrode surface. And so we want to think about non-natural enzyme pathways that really just do the things that an electrochemist cares about. I want to break carbon-carbon bonds and I want to get electrons. I don't need to phosphorylate something and a couple steps later dephosphorylate it. So there's a lot of biology that's there that has a function in biology, but it doesn't have a function in electrochemistry. And so we've looked at ways that we can use promiscuous enzymes to be able to make non-natural minimal enzyme pathways. And we've done that for fuels like ethylene glycol and glycerol, where we've taken some alcohol dehydrogenase and aldehyde dehydrogenase and oxidase enzymes that are quite promiscuous, where the alcohol dehydrogenase will work on all three OH functional groups. The aldehyde dehydrogenase will work on two aldehydes. Oxalate oxidase will cleave both of those carbon-carbon bonds. And we can, with three enzymes, completely oxidize glycerol to CO2. These promiscuous enzymes are also heme-containing enzymes. So these enzymes were actually all isolated and purified from bacteria growing in red wine. And so they're really rich in iron. And so they have a lot of hemes that act as internal relays within them. So not only did they not evolve to be specific like you normally think of an enzyme, but they're also sort of very heme-rich, which allows them to do direct electron transfer very readily. So it's very easy for us to make electrodes out of them. The two of these enzymes, oxalate oxidase and the PQQ-dependent alcohol dehydrogenase, are both phenomenal enzymes to work with electrochemically, but the aldehyde dehydrogenase is not. And so when you start to think about developing enzyme pathways and non-natural enzyme pathways, your first thought goes to Frances Arnold and all of her work with directed evolution. And so we started trying to do directed evolution to evolve aldehyde dehydrogenase to be basically do the chemistry that we wanted it to do versus its natural system. So unlike what Frances usually does, which is directing something to be more specific, we were actually trying to do directed evolution to make it less specific. And we were just really struggling at this. And I went to lunch with one of my colleagues, Matt Sigmund, who's an organic chemist, and he said, Shelley, I don't understand, why are you trying to evolve? Why are you trying to go against nature? Nature's made these, more specific over time. Why are you trying to make them more promiscuous? You should just be using an organic catalyst because they're very promiscuous. And then you won't sort of have this issue. And it's like, well, all of the organic catalysts that you work with in organic solvents. My other two enzymes are not going to like those organic solvents. And I need to get these catalysts to be essentially heterogeneous catalysts on the electrode surface. And so he showed up in my office the next day and he's like, this is your catalyst. He's like, you should give Tempo a try. It will catalyze both alcohols and aldehydes, so eliminate two enzymes. And it works in water. And you spent, your life figuring out how to design electrodes to put things, to immobilize things on electrode surfaces. Surely you can immobilize Tempo on the electrode surface. So we actually gave this a try. Tempo itself did not work, but Tempo with an amine functional group did work to do this complete oxidation process. And then we started thinking about how we could, for all intents and purposes, heterogenize an organic catalyst onto the electrode surface. So we took linear polyethyleneamine. We functionalized linear polyethyleneamine with Tempo to make a redox polymer where basically the tempos are close enough to do self-exchange-based conduction. We can then take this polymer, a cross-linker, some carbon nanotubes, and the enzyme and cast it on an electrode surface. And we do this, we compare the monomer to the polymer. You can see that having it on the electrode surface is really important to having high current density and high power density. And when we looked at all the different sort of substrates that you might want to work with, Matt was absolutely correct that it is quite promiscuous. It can work with methanol and ethanol and glycerol and carbohydrates, both monosaccharides, disaccharides, polyols. So it's very promiscuous from that perspective. So this is giving us a chance to go into looking at hybrid systems where once we get to a situation where we're trying to make that non-natural enzyme pathway, some things just don't do enzyme engineering well. And we can then think about replacing those either with an organic catalyst like I showed you here or with an inorganic catalyst as well. So hopefully in the last 35 minutes, I have shown you that enzymatic biofuel cells allow you to use a wide variety of fuels. I showed you pyruvate and lactate and alcohols and glycerol, but that electron transport is more complex because you don't have a conductive catalyst, and therefore you really have to think about your materials design at your electrode surface. Hopefully I showed you that metabolons are indeed important. And we've got to think about, again, materials innovation to be able to develop electrodes that actually form those metabolones for us. And that every once in a while, you can't enzyme engineer what you want. And that's a great opportunity for you to use hybrid catalytic cascades to do the chemistry that you want. And with that, I'd like to thank the funding agencies, my collaborators, and my research group, because I am just the talking head. And they're the ones who did everything that I showed you today. You guys for being a great audience, and I would be happy to answer any questions you have.
Great, thank you, Charlotte. This is fascinating. So you're basically reducing the biological entities to its bare essential minimum to do these catalytic actions. So any questions from the audience? So let me start. So when you talk about the hybrid catalyst at the end, this is a great idea. So have you considered a hybrid between the enzyme, artificial enzyme with inorganic, right? Because you are in need of an electron conductor anyways.
Yes. Yes, we have. So we have a collaboration with Plamen Atanasov. He used to be at the University of New Mexico and is now at the University of California, Irvine. And so we have been sort of combining some of his nanocluster catalyst work with our enzyme systems. So yes, I think, you know, the struggle with organic catalyst is that most of them operate solely in organic solvents. And the challenge with sort of a lot of the more traditional nanomaterial catalysts is they either operate in highly alkaline environments or highly acidic environments. And so if you think about the enzymes, they're not going to handle those harsh environments. So you have to find catalytic systems that will operate not necessarily at neutral, but will operate kind of in the pH 3 to 11 range.
So what do you think would be the, I'll say, the entry application point for this biofuel cells?
Yeah, so I think, you know, if you look at our continued interest kind of in wearables, so our Fitbits and sort of fitness monitoring, I think energy harvesting is likely going to be sort of one of your first sort of low entry areas. For a number of reasons. One, you actually have quite a bit of some of the fuels that I talked about, like lactate, that are there in sweat, as well as the fact that it allows you to sort of combine something that might be fitness monitoring with also something that may be sort of chemical monitoring for people who are sort of looking for biomarkers.
I see. Great. Right, so I have a question from the other platform. So the question is, they are wondering about the stability of this biocatalyst, and is there any way or approaches to improve their recycling use? Like, can you recycle and reuse them?
Yeah, so that's a really, that's a very good point. So if you take an enzyme and you just put it in solution and let it sort of sit in solution, it's not going to be stable for very long. It's probably going to be stable maybe 2 or 3 days, and proteases will start consuming it, and it will denature and be non-functional. So it's really important to actually sort of encapsulate that protein on the electrode surface so that proteases can't attack it and that it can't sort of easily denature. So again, that kind of goes to thinking about materials, whether those are you know, sort of mesoporous materials or polymer materials that can help you to do that sort of protectiveness. So with the stuff that I showed you today, if you look at the Krebs cycle enzymes, one of those enzymes is a membrane-bound protein, so succinate dehydrogenase. And of course, you're always limited by your weakest link, and that's the weakest link. So those particular fuel cells are only stable for a few days, where the sort of glycerol system that I showed you is stable for months because it's actually protected in a polymer, and they're not sort of, they're much more stable proteins themselves. And so there's a lot of work right now, people looking at extremophilic microorganisms and the enzymes that come from them as enzymes that would be stable for very long periods of time.
Great. Let me check the chat box. So meanwhile, for anybody who's here in the Zoom meeting room, feel free to unmute yourself and just ask away. I'm checking my box here. So while I'm looking, Shirley, so I came across what people are doing this drug discovery when you talk about the encapsulation with the polymer shells, right? So there has been work on when you encapsulate one copy of protein or multiple copy of protein in there. I'm just wondering, has this been explored in the biocatalysis field? So when you talk about metabolons, right? So have you tried to encapsulate those in a kind of a vehicle?
Yes. So there has been a lot of work in different strategies for enzyme immobilization. Some of the strategies of drug discovery work, others do not, because the thing that you have to think about when you're putting it on an electrode surface is that you have to have sort of facile ion transport. So things that would be like ionomers tend to work better than something that is not going to allow ion transport as easily.
I see. So we need to have, I guess, diffusion, right? Kinetics needs to be taken care of.
Yep.
And a lot of, and the catalytic activities. Yep. It's very interesting and very challenging field, I have to say. So if there are no more questions from the audience, let's thank Sherry again for a great talk on biocatalysis. Okay, so I'll move on to let's move on to our third presentation today. So our third speaker today is Professor Shirley Meng. And Shirley received her PhD in Advanced Materials for Micro and Nanosystems from the Singapore MIT Alliance in 2005. And after that, she has worked as a postdoc researcher and then became a research scientist at MIT. Shirley currently holds the Zabel Chair Professor in Energy Technologies and Professor in Material Science and Nanoengineering at University of California, San Diego. She's also the founding director for Sustainable Power and Energy Center, the SPEC, from 2005 to 2020. And last year, in 2020, she's named the inaugural director for the Institute of Materials Discovery and Design. And Shirley's research focus is on the understanding and design of novel electrodes and electrolytes for advanced batteries, solar cells, and thermoelectric materials. And she has received several prestigious awards for his work. To list just a few here, she's the recipient for International Battery Association Battery IBA Research Award. She also just received the Faraday Medal from the Royal Society, Royal Chemistry Society. And she received the Tobias Young Investigator Award from the Electrochemical Society and as a Career Award. Dr. Meng is the Elective Fellow for Electrochemical Society. Also, she serves as the editor-in-chief for the MRS journal, MRS Energy and Sustainability. So Shirley's here to talk about the race for better batteries. So I'll give
Thank you, Yu. Thank you for this very generous introduction. Can you see the full screen?
Yes.
Okay. Yeah, so let me get started. I'm very grateful for the organizers to invite me to this event. The title is The Race for Better Batteries, but I want to emphasize that building better batteries is a global effort. It's not a race among the countries or the continents. It's actually humanity's race against the rising temperature and the CO2 levels. The reason I say that is because 10 years down the road, we will have more than 8.5 billion people living on the planet Earth. We have 6 billion smartphones and tablets, all powered by batteries. And we have about 1 billion cars to be electrified. So there's a gazillions number of batteries that needs to be made by humanity. And it's really, really important that we have a global cooperations for making better batteries so the humanity can win the race for bending the CO2 curve. So let me give a very quick introduction of the brief history of batteries. I think it's important to realize that we, the human race, actually have been dreaming about bottling the lightning since 1748, when Benjamin Franklin first coined the word battery. Along the 270 years, when Sir Volta built the Volta pile, when the French scientists discovered chemistry for lead acid battery, until 1960s, Olshinsky discovered the nickel metal hydride batteries. I want to emphasize that every time when we discovered a new battery chemistries, we make better batteries. We never replace the old ones. If you remember, the more than half of the volume of the batteries is still run by the lead acid batteries today. We only open up new emerging applications. We use batteries to improve the quality of life. And this is really important lesson for me, because think back in history, that 1976 and 1980, when Professor Whittingham and Professor Goodenough built the first generation lithium-ion batteries that's based on intercalation chemistry, which had them earn the Nobel Chemistry 2 years ago. It's really important to realize that the discovery or the commercialization of the lithium-ion chemistry based on intercalation enabled the revolution of mobile devices and electric cars. And for the young generation of scientists and researchers like myself, we need to constantly question ourselves what else we are building to better the quality of life. So the answer is quite clear, because now we have the Internet of Things, the robots, the flying cars, the drones, and more importantly, we would like to build reliable deployment of renewables like solar and wind, and we need energy storage for renewables. So when we set up the right motivations, then we understand why we need to go beyond intercalation. So let me first say intercalation chemistry definitely changed the picture of people about battery. Is just a black box where you have the positive and the negative signage. In fact, intercalation chemistry, this battery has provided the material scientists and engineers a beautiful platform to study materials chemistry and electrochemistry. So give you an example, when I shine the X-ray on a functional intercalation battery, if you shine the X-ray on the cathode, which is typically transition metal oxide, you can actually watch how the volume changes when the lithium gets intercalated in and out of the structure. And you can observe, in some cases, there will be a phase transformation that can be captured by this kind of operando characterization. And this phase transformation is actually completely reversible when you discharge the battery. Okay, so to make a rechargeable battery that has very, very long cycle life, it is of vital importance to people to understand those important concepts that we are moving atoms, we are moving matters. So there are chemical bond breaking and formation. So lithium goes out and comes into the anode. And during this dynamic phenomena, one has to realize, even for intercalation chemistry, there are a few percentage of volume changes happening. And think about your batteries has to go through 1,000 or 3,000 times of those volume changes. A good analogy is to compare the batteries to an airplane that has to take off and landing, because the atmosphere pressure and high altitude pressure difference. So the materials goes through, there's a string events where we'll eventually experience fatigue and you will develop defects, and that's how eventually the battery material starts to fail or start to degrade. The other very important concept in the electrochemistry, one must realize when you build this battery with the anode, cathode immersed in the electrolyte, the protective passivating layer, SEI, is so important, because when you put the batteries at open circuit voltage, open circuit, when you're not using it, the energy retained in the batteries must be stable. So this concept of solid electrolyte interface has been a long-standing challenge for our field. And as we're moving away from intercalation chemistry, for example, the carbon, is a layered structure. This carbon is going to be replaced by silicon or lithium metal. These are not intercalation materials anymore. So how can you ensure the electrolyte is still compatible with the new types of anode or cathode materials is a really, really big question. Because unlike fuel cells, the battery is a thermodynamically closed system. Every carrier you have is actually inside this cell phone batteries that you have. You look at your cell phone batteries, no matters will flow in and flow out of the system. So it's a thermodynamically closed system, and that makes the material science and engineering job extremely difficult because each level, from atomic level to primary particle level to secondary particle level to system level electrode, everything must be perfect. Because if you have any inefficiency that causes the loss of lithium, even 1%, can cause very detrimental effect on your battery's cycle life. And this graph very simply shows the importance of Coulombic efficiencies. When we have a battery that can last for 1,000 cycles, the efficiency, the lithium shuttling between the cathode and anode are highly efficient. So if we are building characterization techniques and trying to decipher where is the degradation happen, this job is very difficult because the change is indeed very, very subtle. We're trying to detect less than 0.1% of the degradation phenomena. So a good example to show you is, my work, this is almost 10 years ago. I mean, it's exactly 10 years ago. But at that time, we were thinking about how can we utilize atomic resolution, scanning transmission electron microscope. I mean, 10 years ago, it's not very common for people to use this kind of so-called very fancy tools to look at the surface of a high voltage cathode materials. And before and after, here you're seeing very beautifully synthesized the cathode particles where you have layered structure. We are calling it a layered structure by cartoon, and actually you can observe in the microscope. And the change is very subtle. After high voltage exposures, you actually see the lithium transition metals, they swapping their positions, but the major phase changes only on the surface 2 nanometers, right? And this phenomena can be easily missing in the traditional diffraction-based techniques, but with this kind of new fancy tools, we can then detect the structural and the chemical change on the high voltage cathode materials. And it's since then, the entire battery field, we always know the cathode particle surface have to be protected with some kind of very robust coating so that the battery can operate a long time on the high voltage. So this is good lesson for, I think for this audience, I can say this, 工欲善其事，必先利其器. So we have developed many quantitative high-end scientific tools to help us to understand from atom to system, where are all the phenomena, dynamic phenomena happening, which ones are reversible, which ones are not reversible. So the few examples I'm going to show you today really shows you the importance of the sensitivity and the accuracy of these tools, because the interface is really the key to control when you put electrode, electrolyte together. And even inactive materials like binder additives play a very important role. And in an electrochemical system, I hope I demonstrated to you their chemistry, there's electrical engineer, there's mechanical engineering issues, and eventually I will also show you their thermal management issues if we want to move beyond intercalation chemistry to the lithium metal cells or solid state batteries. So lithium metal battery is not new at all, right? So why 40, 50 years later, our generation of scientists think we can tackle the problem again. So I think there's a few important things we should realize. The first one is really the power of computation. So this comes from my PhD advisor, former advisor, Professor Cedar's earlier MRS metal talk. He basically grouped all the known materials to humanity at that time to the capacity versus voltage for the lithium-ion system. So just with this simple graph, when I started my 10-year track, I know very clearly these are the areas I will be focusing on because this is the region where you can achieve very high capacity and a very suitable voltage for the existing electrolytes. So this is one of the key enabling factors, in my opinion. Computation and the power of supercomputers can save us quite a few years to actually think about the next generation materials. So on the lithium-ion battery side, the next generation materials, in my opinion, are these anion redox oxides, where you can have 30 to 40% energy density increase compared to the classical layered oxide. But just the battery performance itself is not interesting, right? What interests the scientists is what are the new science that enable us to store more lithium, store more energy in the matter, right? So this is where we utilize the state-of-art coherent X-ray diffraction, because the coherent X-ray diffraction can enable us to detect the strain during intercalation and to detect the defects such as dislocation and screw dislocation or edge dislocation generated during the electrochemical operation. So the classical materials and the new anion redox materials has completely different tolerance to the defects. And the defects is, for material scientists, the defect is good defects or bad defects. So if you have the defect density actually engineered correctly in the particle can actually indeed store more lithium and actually release more lithium reversibly and give you more energy density. So this kind of breakthrough in the energy density for the cathode materials is so exciting for us. I mean, there was widely criticized that this material has a voltage fading problem, but right now I think this voltage problem is completely under control because we now understand defect play a very important role in the voltage decay. By controlling the defect density, we can actually control the voltage decay, and we can predict the voltage decay. So if I show you the roadmap of what's going on for intercalation chemistry, even though the Nobel Prize is already given, I think it's really nice to think about what did our field do in the last 20 plus years, right? Because we didn't change, I mean, we stayed with intercalation chemistry, we changed the cathode materials, right? Just by using the graphite anode, we were able to triple the energy density. And thanks to the, the economy of scales, particularly the contributions from Asian countries, the cost has reduced more than 10 times since the time I have graduated. I mean, when I graduated, the lithium-ion battery pack cost is $2,000 per kilowatt hour. I would never imagine that, 15 years later, it's less than $150 per kilowatt hour. And I think the solar field is seeing the same trend. It's truly, truly exciting. I think if you look at this roadmap that's established by US Argonne National Lab, I think it's very good to have a roadmap and think about what we need to do to enable the next big jump in energy density. So if you look at the energy per weight and the energy per volume, let's not argue about the exact numbers, whether they are on the cell level or system level. The important thing is the ranking, right? So what's being commercialized and what are in the pocket of scientists, because we have demonstrated that the lithium metal paired with the anion redox materials can give you very high volumetric energy density batteries. And if we pair lithium metal with the oxygen or sulfur-based cathode, we can really, really take off in the gravimetric energy density. These kind of batteries are very, very good for flying cars like drones, right? So those roadmap tells us very clear message: lithium metal anode must be enabled. So that led to our 2016, a consortium-based research that's led by Dr. Jun Liu from Pacific Northwestern National Lab, and included both Professor Whittingham and Professor Goodenough in our consortium. So if you look at the lithium metal batteries, again, you know, for young scientists, please read the 1976 science paper. I think I love those kind of publications that 50 years ago, everything in that paper is still correct. Right? So in the 1970s, when Professor Whittingham built the first lithium metal batteries, the cathode has no lithium in it. It's titanium disulfide. So for this reason, he needs to put a very thick block of lithium metal on the negative electrode side. Our situation is completely different. We have high lithium containing lithium cobalt oxide, lithium iron phosphate, or lithium nickel manganese cobalt oxide. So today, when we build the third generation, so I call it the third generation or second generation lithium metal cells, you can actually see that we can afford to put a very thin layer of lithium metal because the new electrolyte discovered by Pacific Northwestern National Lab enable us to deposit and strip lithium with very high efficiency. So in theory, you can have anode-free. But of course, you know, anode-free has other problems, you know, but I will just say like we just need ultra thin lithium metal because most of the lithium will be contained in the NMC side. So if you use sulfur, you still have to use thick lithium metal. I won't touch this topic today because the focus will be on the lithium metal. So again, let me brought back to my major message is 工欲善其事，必先利其器. Okay, so why in the early days, lithium metal characterization is so difficult? So I show you an example. Literally, lithium reacts with everything. When I say everything, it means nitrogen, oxygen, carbon dioxide, water. Lithium reacts with everything. So when we do scientific instrument, even you use the focused ion beam to try to cut a fresh surface of lithium, the gallium ions actually alloys with lithium at room temperature. So if you do a room temperature cut of the lithium surface, everything you see here is artifacts. It's not the lithium surface that you're seeing. If you actually do cryogenic condition, the kinetics of the interaction will be dramatically reduced. And that's where you can actually get a quite clean surface of the lithium metal. This lithium metal is, of course, a you know, just a metal sheet. So it should supposed to be dense and very smooth and very nice looking. Now, why this tool is so important? Because electrochemically deposited lithium does have a lot of pores and tortuosity. So if your tool already interfered the lithium, you cannot observe lithium very well. That's a very easy logic to follow, right? So with this advanced tool, we can now cut lithium slice by slice in the fib, and we can do three-dimensional reconstruction of electrochemically deposited lithium. So in the electrolyte that scientists have been optimizing for graphite anode, carbonate electrolyte, we also call it the Gen 2 electrolyte. It's terrible. The morphology is terrible, okay? You can actually take the top view and the cross-section view and you do the three-dimensional cut. It's really quite terrible. And the performance, I think the efficiency number is very low. So 98% means, you know, after a few 50 cycles, you have no capacity anymore. Everything is lost, right? When you have new electrolyte based on you know, what the Pacific Northwestern National Lab has reported in the ether-based electrolyte, the morphology completely changed. You have very dense lithium. I mean, it's not perfect yet. I will talk to you later about how to make it more perfectly dense, but these cells actually reasonably much better than the carbonated electrolyte, right? So in order to understand why morphology is so important, I want to show you this transmission TEM picture, and it's obtained under cryo condition. You cannot obtain this kind of very high resolution image in the regular TEM because these metallic lithium are actually surrounded by the insulating SEI. So SEI contains lithium oxide, lithium fluoride, lithium carbonate. It's very insulating. So when you put the high energy beam, electron beam on it without the cryogenic condition, so it's not just the temperature, cryo-TEM also use very low dose and a very high detection efficiency detectors, right? So under those conditions, you can image lithium metal and you can actually see if you have large granular particles, you have very little lithium gets stuck in the SEI. But if you have those kind of tortuous, very elongated, high aspect ratio lithium metal, it's very highly likely you will run into the situation where the lithium metal lost its structural connection with the current collector. So electrochemical, right? You need both the ion pathway and you need the electron pathway. So if the blue part SEI is too insulating, you cannot actually access the very good electrochemical system. So that's the reason in our Nature paper, we hypothesize that the SEI is not the major culprit for low efficiency lithium metal battery, but the microstructure control is. And to emphasize this important discovery, we also complemented the TEM data with this new titration gas chromatography measurement. The principle is quite straightforward because of all the SEI component, lithium metal is the one will give you hydrogen. So we only need to measure hydrogen amount. So when we measure the hydrogen amount, we found a very interesting phenomena that agree with our hypothesis is that all the capacity loss is perfectly correlated with the metallic part of the lithium, not with the SEI. So I want to emphasize here that, of course, some of these Coulombic efficiency numbers are so bad is because we deliberately chose electrolyte gave very bad Coulombic efficiency to prove the point. So when people now are working on the high efficiency electrolyte, I want to emphasize the SEI is still very important, right? So this work is already 2 years ago to showcase that, first we need to understand, we need to control the microstructure of the lithium metal, and the SEI is not the main reason for the low Coulombic efficiency of lithium metal batteries. So because of this discovery, I think we can now think about other effective strategies to ensure the 100% reversibility of this lithium metal deposition and stripping. So one of the most important successful example we have shown. So we worked a little bit on 3D current collector. I don't have time to go through today, but I will just show you that with the pressure control, right amount of pressure control, we can very successfully deposit. This bar is 2 micron, okay? So we are actually depositing 20 micron of dense lithium and strip this lithium under a very moderate pressure level. And all this knowledge has been translated into real 2 amp hour cells that is made by Pacific Northwestern National Lab. This has been released to the public that, in 2017 when we started, I told you we can barely cycle 50 cycles. And today, Battery 500 is reporting more than 500 cycles for the lithium metal cells. So again, I want to emphasize the battery performance is the consequences of doing the right material science. So in this case, I hope I showcase to you that lithium metal anode is a very promising pathways forward. So the second example I will give you is really anchoring towards, many young students coming to my group to study, PhD or master degree in energy storage. They ask me, what are there left to do? And in my mind, there are so many more problems that we have not resolved yet, even though that lithium-ion batteries is a $50 billion industry now. But in fact, we have a lot of unanswered challenges to the public. For instance, a battery with very high energy density, but never catch fire. So right now, the accidents rate is 1 in 10 million. So we ship out about 1 billion cells of our industry. We still have, accident here and there. So it's not good enough. We admit this. We need to do better. The other thing is, the solar cells now can last 30 years. I always get a request from, people who have installed the Tesla wall. They were like, how long that's going to last? When I tell them maybe only 7 to 10 years, they were pretty upset because, the solar panels guarantee 20 years of lifetime, right? And then we also are seeing the huge demand in battery recycling. And I think in United States, I think people are very impatient going to the charging station. So 30 minutes is not good enough. They want to do fast charging. So all these topics, in my opinion, for the young researchers or new researchers, everybody is young, okay? If you want to change field, so you're young researchers. So for people who wants to come into this area, I think there's plenty of work to be done because the electrification of our society is an unstoppable trend, and we need to do better in terms of safety and performance. So the allure for all solid-state batteries is quite clear because I just show you a few the videos, right? Actually probably in this video is more clear, bigger, right? Just show you some tricks that you can play with all solid-state battery. You can cut it, you can bend it, you can abuse it, and there's very low fire hazard. I won't say it completely will not have any safety accident, but you can never do this with the liquid cells, right? And you can also widen the temperature of operations that the batteries can operate at a pretty high temperature. So this is the, the consequences if you can actually enable solid-state batteries. But the unknown question is pretty clear because, we improve the properties and nobody can guarantee at the moment that the cost is down, right? So for the batteries, we always talk about the cost-performance ratio. So I would say we should never be driven by, okay, this is the next best batteries. Instead, all the people should actually really think about what interesting material science and electrochemistry I can do. Now I have a new platform with solid-state electrolyte. So the difference between liquid and solid is that in the liquid electrolyte, I have intercalation materials like graphite and traditional metal oxide. They are stable in the homo-lumo level of the liquid electrolyte. When I cycle the cell, of course, there's SEI. Now, in the solid state, we have a big trouble because the anode is lithium metal. We want to enable lithium metal, right? And I just tell you lithium metal reacts with everything. And that everything include many of the polymers and the sulfides. Lithium is indeed stable with LLZO, garnet type of solid electrolyte, but that's a very rare cases, right? So number one, material scientists have to think about how to make them chemically compatible to stabilize the lithium metal anode in the solid, okay? Number two, of course, you have another challenge. The solid usually has very narrow electrochemical window, so you still have the SEI challenge. Number three, the more problem for solid is that in the liquid cell, the liquid can flow freely. Whenever you have something, the liquid will flow in. Now in the solid, if you have during the synthesis, you have a void, you have an empty space. That's not good during the synthesis because you have created a lot extra interface. So in this chemical review paper, we said you have at least 6 extra interfaces compared to the liquid electrochemical cells because you have, the void can also be playing a very important role. And for this reason, in solid-state batteries, mechanical compatibility or mechanical properties become such important topics beyond just electrochemical interface, right? So if it's an interface stabilization, I can apply many tricks like coating materials, and I can, because 10 years experience in cathode coating, I think we are quite comfortable to do the coating. But this mechanical strength is something really, really surprised me. Okay, so in terms of coding, I want to say that coating, like 5 to 10 nanometer conformal coating, the material scientists have many ways to achieve that. And indeed, with the sulfide-based electrolyte and the nickel-based cathode, if you do not engineer the interface, you cannot actually utilize the cathode very well, and you cannot cycle the cell very well. And this particular coating here is a lithium niobate oxide, which was released by Toyota many years ago, and they already have patents, solid, right? But the problem is they are not same mechanical property. Lithium is soft, sulfide is not so soft, but still, a little bit malleable. Oxide is very hard. So during the synthesis, you need to do a contact increase by increasing the pressure to 25 megapascal. That reduces the contact resistance dramatically. But during the cycling, if you don't release the stress or release the stack pressure, you run into a problem called the mechanical induced shorting of the lithium, because the lithium will creep into the cracks in the solid state electrolyte. So when we find that, it's to our surprise, the lithium metal anode only cycles when you release the pressure to 5 megapascal. But if you have complete pressure free, like if you don't add any pressure, you also cannot cycle the cell. So we are only at the very beginning of lithium metal based solid state battery, because even though here, in publication, I can show you this is quite a stable cycling. The point here is to prove stability, but the performance, this rate, I'm moving the lithium ions 10 times slower than the liquid case. And that's how I move slowly. This whole experiment takes 3 months to complete, right? So the mechanical, optimal mechanical setup for the solid state battery is still a largely unresolved issue. On top of that, I would say, as someone who works on characterization, I am facing a lot of challenges because these interfaces, because they are all solid state, so they are completely buried, right? Not only that, but these lithium containing materials are extremely sensitive to air, to nitrogen, to moisture. So the characterization become a very, very difficult task. I think recent years, CT, fib cutting, they become very important tools for us to look at these buried interfaces, but it's pretty challenging, I would say. So if I have to give a quick summary of what happened in the solid state battery field, I believe in terms of ionic conductivity, we have plenty of candidates. Sulfides, oxides, halides, just 2 years ago, the halides reported record high conductivity numbers. Now, our challenge for interfacial stability is being well addressed because we developed quite a lot of advanced characterization method. In terms of mechanical stability, I will put a question mark here. And more importantly, because we are switching from liquid electrolyte to solid, how the processability and scalability look like is still a big question mark, right? So if I only need to focus on the positive side of the solid state battery, is that, in the past, room temperature sodium solid state batteries is not accessible. Today, with all the discovery of new halide-based solid electrolyte, it is possible. This is a new phase reported earlier this year by my colleague Shiping Ong and I. We made these new yttrium zirconia chloride-based halide sodium room temperature sodium solid state batteries, solid state electrolyte that can enable quite stable solid state sodium ion batteries cycling, right? So this is, of course, far away from commercialization because we are only conducting in tiny little lab scale cells. But the exciting things, again, is we find ways to discover new superionic conductors and find ways to do better interfacial engineering. So I think with that, I would say, let me bring my talk to a finish line. I have been extremely blessed with brilliant students and postdocs who contributed to all the work I have talked about, and we are very blessed with the DOE, both basic science, because a lot of the characterization tools takes years to develop, as well as the vehicle technology offices for the cell prototyping and things related to that. And also our industry and national lab partners. I think I will have time to take a couple of questions, I hope. Thank you very much for your attention.
Thank you very much. This is really impressive work. I really like you have to really get to the bottom of the problem, the material science problem, in order to better the design of the battery electrodes. So first of all, any questions from the participants in this room? You can unmute yourself and just ask the question. Hi, Yuri, go ahead.
Hi, Shirley.
Hello,
very inspirational talk. I'm wondering whether you think that polymers or other faster systems than chalcogenides or oxides can be competitors for the solid electrolyte markets.
Yeah, thank you. Yeah, so I guess let me just use this graph to explain what is the status of the solid state electrolytes. So I believe that the polymer will play an important role in terms of addressing the mechanical stability and interfacial stability. Now, if you look at this dotted line here, that's the liquid LPF6 line. So a couple of our solid state electrolyte is only 1 magnitude away in conductivity compared to the liquid electrolyte. Now, the difference is the transference number. So in solid state, the transference number is very high, but in the liquid, they are low. So for polymer, I think there are still debates if polymer is really single ion conductor with very high transference number. I hope Natasha is not listening, but I mean, there's a debate. So to me, at the moment, even if polymer has very high ionic conduction, I need a high transference number, because the problem is if the anion is moving together with the lithium, you always have this challenges for the kinetics, like for the impedance of the cells. So yeah, I think it's still an ongoing research topic. I do think that in order to make thin, flexible membranes with these ceramic materials, polymer must play a role. So whether it's lithium conducting polymer or non-conducting polymer, that's open for debate. But I think polymer will definitely play a very important role in the solid state batteries.
Thank you.
Great. So I have a couple questions from the other platform. The first one, I'll go with the first one first. So the question is regarding the cathode materials. What aspects of research might have more potential, like looking forward?
Oh, yeah. Thank you. A very good question. So today I didn't have too much time to talk about the challenge for the cathode electrolyte interface. Okay, so maybe I can use this picture to explain. If you look at this bulk cell characterization, this is a pristine material. So the cathode, right? The challenge is really, even for intercalation cathode, they experience 2 to 4% of volume change. Okay, so if the volume change happens and those cathode detach, because they are shrinking, right? So shrinking or expanding, if they detach from the solid electrolyte, then you lost contact. And because it's solid state, the electrolyte cannot flow, and that will increase your cathode electrolyte interface impedance. So this is actually, to me, the single most critical problems for the cathode, and which is still not resolved. So I think the person asked the question is really an expert. So this is an important area that all the people who are on the cathode side of the solid state batteries have to worry about. It's very, very difficult to find a low or zero volume expansion cathodes so far.
Great, thank you. Any other questions from the Zoom room? If not, there's another question regarding the self-discharge performance in solid state or solid state batteries. Mm-hmm. Can you comment on that? Yeah.
Okay. Yeah. So at the moment, so I think the solid state batteries field has not reached the maturity level of doing proper calendar life assessment. So I think at the moment, at least the lithium interface with the solid state is stable under the, I would say, the current test conditions. But as I reviewed that everything is in very small scale cells, so the area is very small, right? So I think until we can build a very large pouch cells, large area pouch cells, we can then do the proper measurement. But I do want to maybe take this opportunity to address this lithium metal, this corrosion problem for the lithium metal, even in liquid. I want to clarify. If you have this kind of very densely packed lithium metal, the corrosion problems or the self-discharge problems is very minimal because there's almost no contact except for the top surface, which already have all the SEI formed. There's almost no direct contact with the fresh electrolyte, and we can actually, keep those cells functional and low self-discharge for months and months. And these kind of cells has already been demonstrated in large format. So they have proper evaluation of the self-discharge. So yeah, for solid state, it's still a little bit early, but I think in the end that this question has to be addressed.
Thank you. I have another question. I think maybe the last one here.
Sure.
So what else is left to be studied in the field? So conventional LFP and LCO. I'm sorry, I'm not in the field, so I don't know what those meant.
That's very good. Yeah, that's a very good question. Thank you for the great questions. Actually, the audience, I really appreciate it. Yeah, so for me, the LFP and LCO, for me right now, fast charging. And it's I didn't have time today to address this topic. For me, this is really, thermal, mechanical, electrochemical, like three coupled phenomena. And I think to push materials like LCO and LFP to the extreme is something very, very fun to do. So I believe that, the future cell phone batteries will all be charged in 5 minutes if we can do this right. Even though, I think from the chemistry perspective, maybe there's not a lot to be done, but from the thermomechanical property perspective, there's a lot more to be done for the LFP and LCO.
Great, thank you. And so thanks, Sherry, again for a very excellent, stimulating talk. So let's now move on to our the fourth and the last presentation for this session of the workshop. So our fourth speaker is Professor Lianzhou Wang. He is the professor and Australian Research Council Laureate Fellow in the School of Chemical Engineering. And also he's the director for Nanomaterials Center and senior group leader for the Australian Institute for Bioengineering and Nanotechnology at the University of Queensland. So Professor Wang received his PhD degree from Shanghai Institute of Ceramics in the Chinese Academy of Sciences at 1999. And Professor Wang's research focuses on the design and applications of semiconductor materials for renewable energy conversion and storage, including new photocatalysts for solar cell hydrogen production, and also low-cost solar cells and energy storage systems. He also has a long list of accomplishments, which for the sake of time, I will just leave it to his excellent talk here on semiconductor nanomaterials for PEC energy conversion. Professor Wang.
Okay, thank you very much, Professor Huang, for the nice introduction. Before I start, I would also like to thank Professor Guozheng Tou and Professor Dr. Guilin Wang for inviting me to attend this wonderful workshop. I learned so many wonderful talks in past 2 days, and for a bit different from the previous three talk, and today I will be giving a brief update on what we have been working on in the solar energy conversion area, and in particular the photoelectric chemical hydrogen production. So why hydrogen? I think the background, we don't need to go through the details and to address the climate change challenge, and we really actually need to have a sort of a cooperative efforts globally and to push to the renewable energy use. I think hydrogen as a clean energy carrier is certainly stand out as one of the most promising approach and to address the climate change issue. And in this, in terms of the hydrogen production, currently, unfortunately, most of the hydrogen have been produced by the gas reforming process. And in the short term, I don't think there's any technology can compete with the renewable, the reforming gas reforming process of hydrogen because of the cost. But in the middle term, we are looking at some other approach like biomass production of hydrogen, and we can also use some renewable electricity, like the electricity generated from wind and solar, and plus some electrolysis, and to drive the process to produce hydrogen. While if we think about the long term, in large scale, more sustainable way, we really need to learn from our nature, Mother Nature, and to think about the way that's actually like mimic the nature's photosynthesis process. And for hydrogen production, that's actually a photoelectric chemistry, a chemical process, biological process, or thermal and plus some other chemical approach. That's what we are interested in, and we're really interested in the artificial photosynthesis process. And this is a very simple way, not include CO2, and that's for water splitting and to produce hydrogen. And if you look at the solar hydrogen technology, certainly there's some current the options, like as I said, and currently in terms of the production efficiency and the cost, and so the photovoltaic plus the electrolysis and certainly have high efficiency, but it's also the cost is relatively high. And if you only look at the electrocatalyst area, there's so many researchers worldwide, I think, very busy area as well to develop some new catalysts. So for the water splitting approach, and if you go this direction, and the price and the cost can be relatively cheap, but unfortunately, and the efficiency for hydrogen production is quite low. And what we really want to do to push actually towards this direction, and with high efficiency and lower cost. That's what we do. We have been working in this area in photocatalytic platform, and also the photoelectric chemistry approach, and to address this issue. And I think that in the middle, in the middle of the research is this semiconductor materials nanocatalyst, and it's had good interaction and between the light, and it's absorb light, and then to generate some charge carrier. And if it's the charge carrier are not recombined, recombine, and it will have the luck to transfer and to the surface of the particle to attend a number of reactions, like photo-induced reduction and oxidation reaction. And so if we can have good management of these three key steps, like light harvesting, charge separation and transfer, and also the surface reaction, and we have good hope actually to achieve good efficiency. But unfortunately, and so far, and the efficiency is very low, and only in a single digital. And what we really want is to achieve the solar to hydrogen efficiency at least 10%. Why 10%? That's because actually the current gas reforming process to produce hydrogen is pretty cheap, and we really need to have a very good efficiency and to be compatible with the current technology. But if you look at the key process of the photocatalyst process and the reaction, and you can see actually it's cover a very broad time scale, and from the light absorption to the surface reaction, and it's it's cover a broad scale, and that's also generates a lot of opportunities for the charge carrier to be lost, to be combined, and actually cannot get efficient surface reaction to happen. And in the powder form, actually, we also have the challenge of if you have photocatalyst and in suspension, you have hydrogen and oxygen produce a mixture, yeah? And it's a two-half reaction. And this basically is pretty dangerous as well. We also need to have separating approach. And then we really want to develop some, the PEC approach. That means we have two catalysts, one oxygen production catalyst, another is hydrogen evolution catalyst, and separately and on two electrode, and in between there's a membrane, actually two chamber approach, and to produce hydrogen and oxygen. And in this approach, basically, the photoanode side, that's for the oxygen evolution, is still the key because it involves 4 electron reaction, and so this is the bottleneck. And we in the past couple of years we have been working on the catalyst design and try to address these 3 key issues, like the how to improve the light absorption, and this actually is related to the material design, the doping, band gap engineering, and selection of the good materials, and the surface. And the second step is such as the charge separation and transfer approach, and that's really it's up to the interfacial engineering and also the defect design, and the surface reaction is also needed to choose good catalyst, and so to actually to find the reaction kinetics to be performed better. And I will just actually give you a few examples in the following slide to show what we have been working on and try to further improve the efficiency. So, and if you look at this chart, basically in terms of the carrier candidate, and as I mentioned, the photoanode is now the bottleneck, and it's basically highlighted as red. And if you can see, most of the available photoanode, they have relatively low photocurrent. This is related, actually, this can be transferred to the efficiency, solid hydrogen efficiency. And if you really want to target the solid hydrogen efficiency of 10%, that's basically we need to reach around this level. But unfortunately, actually, if you look at most of the available catalyst and photoanode, and the like TiO2 and tungsten oxide and some other oxide materials, they have still have relatively low theoretical photocurrent performance. But we're still interested in this category. The reason is that if you really want to have solar hydrogen to be produced at a low cost, and also in stable, we really need to use this cheap material and stable material other than just this type of 3-5 group, very expensive and unstable material. So we started with some classic TiO2 based material, because this is in photocatalytic area, this is the I think most studied materials. And we started with some layered compound actually for the TiO2, and delaminate this into nano sheet of TiO2, a single layer, and we use this to layer by layer to assemble the electrode and try to test the performance of the TiO2 based photoelectrode. And for example, this one we use layer by layer in combination with some polyaniline as the binder. But unfortunately, we found that the photocurrent generated onto this TiO2 based electrode is terrible. And so, of course, we found some other interesting phenomena like the switchable photocurrent. But in terms of the the scale of photocurrent density is basically it's a micro ampere per square centimeter. This just barely about 1% of the theoretical capacity, theoretical photocurrent of TiO2. So then we have been thinking why actually TiO2 material can only achieve this small photocurrent. And basically the two things. The first thing is actually the charge transfer pathway on this layer by layer assembled nanosheet is not that good, because in between there are some polymers to possibly block the charge carrier pathway. The second one is the film is very thin, and it's actually not able to absorb too much light. And then the question come up, and so can we use the same material TiO2 and by structure design and to improve the PEC performance of this material? And then so we changed the approach and still working on this layered TiO2 materials, but actually we use the hydrothermal process to grow the TiO2 some nanoplate vertically and actually on some FTU glass, for example, in this case. And we also found some interesting phenomena, and because actually in this nanoplate there are a lot of porosity, and this can be very good because actually if you really want to have the charge transfer and for surface reaction in photocatalytic process, and the diffusion distance of the charge carrier can be very short if you have a lot of porosity, and you also have personality. And we also actually try to understand the mechanism of this type of structure formation. I will not go through the details, but what we are more interested in the photocurrent actually generated onto this electrode. And if you look at the photocurrent of this this TiO2 electrode, and basically it can going up very quickly and to reach about 1 milliampere per square centimeter. It's pretty close to its theoretical current, and in a very short potential window. And that's actually, if you look at like the field factor things, and it's also very good. And that means actually the photo separation and the transfer behavior of this material is very, is much better than the previous nanosheet based one. And and this certainly gives us some indication that's the same material TiO2, and if we can tune the structure, and we can possibly maximize the photocurrent of the materials. And another approach we used is not to only to the structure, but also try actually to build some additional sort of electric field in the photoelectrode. So in this approach, we continue to use TiO2 and and we borrowed some idea from the lithium-ion battery. That means we do some insertion of the lithium-ion into the TiO2 lattice. And why we are doing this? Because in the photoelectrode, PEC approach, normally actually we have a TiO2 film, and there's an electrolyte on the interface. There's a band bending, and this band bending will provide some good driving force for the charge carrier to be separated, to be transported. But if we have a relatively thick TiO2 thin film, and in the back of the film, and actually the band is still flat. That means actually the driving force for the charge separation is not that significant. And in this approach, we try to have a built-in electric field across the film. And the idea we use is try to insert some lithium into the TiO2 framework, And so because they were only going to the void around here, not go to into the octahedral. But actually, because of the insertion of the lithium, and it will distort the octahedral of the structure, and then to have some dipole moment. In this case, the building it have some built-in electric field, so on the in the electrode. And so we use a number of characterization to understand actually upon the lithium insertion, we certainly see, and in some direction, actually the like the 004 direction, and the size actually had been squeezed, and the other direction 200 had been expanded. That means the octahedral has been distorted. And we also applied some contact potential difference. So upon in relation with the light, and to see the difference after we insert the lithium into the system, and we already found some of the built-in electrode, so electric field. So in the lithium inserted TiO2. And which basically provide a good driving force and for the photocurrent to be increased compared with the inserted ones, and in this case also reach relatively high photocurrent density. And this also give us another example. Actually, when you structurally or compositionally tune the materials, and you are able to reach relatively high performance, so in the same type of materials. But as I said, TiO2 still have a very wide band gap, and basically it cannot reach very high PEC water splitting performance. So then we also turn our attention to some narrow band gap materials. So in this case, it's bitumen 1 oxide photoelectrode, and we use the similar approach. Hydrothermal treatment to prepare the electrode, and in this case we applied a very minor, very small negative bias to the system for maybe around only 2 or 3 minutes, but we found actually quite an interesting phenomenon that so upon the electrochemical treatment on the electrode, and we can see very significant photocurrent increase, and this going up to actually around 3 milliampere per square centimeter in this case. And we also try to understand why and such electrochemical treatment and can increase the photocurrent. And basically we found the electrochemical treatment so partially and so reduced the transition metal. So in this case, like bitumen from 3+ actually to 2+, and 1 to 5+ actually was reduced to 4+, and in this case generate some oxygen vacancy, and this oxygen vacancy can form some can behave like the cell donor level, and to improve the charge separation and transfer property and in the system. So this gives you some implication that actually oxygen vacancy in the PEC water splitting approach can play a very significant role. And so indeed we want to further understand so then so more thoroughly about the oxygen vacancy in the PEC process. And we pick up a single keyword like photoelectric chemical. And if you look at this word, and it basically can be split into two. And the first one is the photovoltaic effect, and the other one is the electrochemical. And so then we want to actually decouple this PEC approach into two processes, and to understand better about the tuning like oxygen vacancies effect onto the PEC performance. And in this case, we choose another narrow band gap semiconductor iron oxide as an example to showcase the role of the oxygen vacancy. And in this case, we intentionally introduce so a different type of contents of oxygen vacancy, and in the iron oxide photoelectrode. And basically, for the oxygen vacancy, there are a lot of study before, and the commonly accepted role is that oxygen vacancy can actually certainly help increase the bulk transportation of the charge carrier. And we also found that the similar trends. And so if we treat the electrode in the nitrogen atmosphere for different times, we found actually the photo current generated onto the electrode have quite a big improvement compared with the untreated ones. But actually, there's certainly some maximum optimized condition. That means in certain range of the treatment in nitrogen atmosphere, that means you introduce different amount of oxygen vacancy, and the photo current certainly can increase. That's the charge carrier concentration can increase, but only to certain range. After it's reached a maximum, and actually the photo current will start to decrease, and that's basically means. And in this photo PC water splitting process, the oxygen vacancy role can be more complex than they previously reported. And so, and then we started to look at these two, decoupled approach. The first one is to look at the surface reaction. Surface reaction basically is an electric catalytic process. And we use a number of characterization tools, including the simulation tools to understand. We found actually the introduction of oxygen vacancy on the surface certainly can lower the formation barrier of the oxygen and to have a faster kinetics. And then we continue to look at the PV effect, photovoltaic effect, and this effect is more interesting. And if you look at the photocurrent generated onto the oxygen vacancy containing electrode, certainly it has high photocurrent, but the VOC and the open circuit voltage has been decreased compared with the electrode without oxygen vacancy. And we also look at some other performance like charge separation difference, and we found actually there's quite some difference in between these two electrodes. And what does this mean? This means, and in the whole process, and if this is the electrode, photoelectrode, and in the bulk, and basically, after we introduce the oxygen vacancy and the charge carrier, and are able to actually transfer more efficiently. But on the surface, on the surface, and the oxygen evolution process, the kinetics can be faster after introducing the oxygen vacancy. But in the middle, that means on the interfacial area. And because actually we introduced the oxygen vacancy, which will behave like some trap state. That's basically it's block the split of the Fermi level, like the Fermi level that is related to the VOC. As I said, here VOC is decreased. Yeah. And so in this case, and because of the reduced VOC, the driving force for the charge separation is not that significant. In this case, and on the surface, and the oxygen vacancy play detrimental role. And overall, actually, in the bulk, it's good, and on the surface also have a good role, but in the middle, actually, it's really have some damaging role, and we really need to have a very good balance and to modify and the electrode, and by tuning the oxygen vacancy position and also the composition. So we also extended our study to some other system like a bismuth-validated electrode and also the photocathode, and we also found some consistent role of the system and in terms of the vacancy control for the PC performance increasement. But the final actually target is still to increase the overall efficiency in terms of water splitting. And in this case, actually, we used the photo Bismuth 1-liter electrode, a semi-transparent one, and we try to achieve as high as possible photocurrent. And by using this one as the electrode in combination with a solar cell and without any external bias, and we found actually the system can produce hydrogen and oxygen and a relatively good efficiency of around 6.5%. And so this is so relatively good good results for the PV PEC like a tandem system. But if you think about the solar to hydrogen conversion target, and we still actually have a long way to go. And if you look at this curve, and basically the solar cell can produce relatively high photocurrent. This is the working point. This is related to the efficiency of 6.5%. And if we really want to further increase the efficiency for solar hydrogen production, we really need to push high on this side. This red curve. This red curve is related to the photoelectrode actually we developed. And we also recently we turned our interest actually to the perovskite, and the perovskite, you know, is in the solar cell sector. It has been a great materials, but we found it's actually satisfy almost every criteria for the PEC water splitting, and except the stability things, and because it has a very long charge carrier mobility, and the tunable band gap, and also the light absorption coefficient is significant. So there's actually a lot of good ways, and we also try to use this one and to see whether it can do something in the PEC water process. But before that, actually, we first actually need to develop such type of perovskite. And recently, we developed a new class of quantum dots actually of the perovskite, which have quite a unique, quite good shape, and also tunable band gap by changing the composition. And because these quantum dots have a lot of unique feature compared with the bulk counterpart, like the multiple excitation generation, also very good stability and to suppress the ion migration. And we use a new called ligand excitant so cation exchange approach, and to produce a mixed cation like cesium and Fe based lead iodide cation lead iodide quantum dots, and very efficiently and in a very short period of time. I will not go through the details. And by using this, we can prepare some device, and because quantum dot solar cell, and this which has a very good efficiency and certified, and it's been recognized in this real chart, and unfortunately. So in this one, and what we really want to show is the stability of the materials. And so, as I said, because these quantum dots have some ligand and actually on the surface, which can provide a good way actually to protect and protect the quantum dot from phase segregation, and compared with the bulk phase, and we can see the quantum dots upon the light soaking for 4 days, it doesn't show any difference. And in terms of the long-term stability, and after 600 hours, and the light, so we still have more than 90% of the original efficiency. And so this also have been, so highlighted by the journal, saying that's how to balance the stability and also the efficiency of the system is critical. And by using the same idea, and we we try to introduce the the quantum dots for the perovskite and into the photocatalytic system. And in this case, we also have a good engineering of the surface ligand of the quantum dots, and which actually on one side can protect the quantum dots from decomposition. On the other side, will also not block the charge transfer between the quantum dots and the TR2 in this case, and which have good photocatalytic hydrogen production yield. And in this case, actually, for the mechanism-wise, actually, we found appropriate amount of the surface ligand play a significant role and in balancing the stability and the performance of the system. And for the more detailed things, I will not go through. And so with this, I think I would summarize. And what we really want to highlight is the importance of the material design, material selection, and which will play a significant role in the electrode and the system, and so for the solar to chemical conversion application. And there's a few recent review paper, and you can have a look if you have interest. And with this, I think I would like to thank my colleagues, a number of colleagues actually from China as well, and this is my team. And thank you very much for your attention.
Great, thank you very much. It's a great talk about material design integration for performance. So any questions from the audience here? I can, before I move on to the other online questions.
Lian Zhou, Hongjin here.
Oh, shit. How are you?
Hi. Very good. So thank you for the nice talk. I just ask about the last part, using the perovskite quantum dot as a light absorber. So quantum dot light absorber has been a very old story, but it's based on those kind of cadmium sulfide or lead sulfide quantum dots. So compared to your new perovskite-based quantum dots, what do you think is the advantage, and compared to those old conventional quantum dots?
I think the advantage of this one certainly is still its light harvesting performance. And as I said, so this perovskite materials has much larger the light absorption coefficient compared with the other. So this is one thing, and the other thing I think is the charge injection performance, because it's I think this one has a very good light harvesting and charge separation and transfer property, which will help. But the difficulty is the stability of the material. In this case, we use gas solid phase reaction. But more recently, actually, we have developed a new approach and try to immobilize the perovskite and into some composite, like MOF composite, and which certainly have much better performance with, I think, the stability, and putting some water for 10,000 hours still have the capability.
But like the old conventional quantum dots, they can have this rainbow effect, right? They can tune the band gap, so it can absorb wide broad spectrums. Is this also possible for the perovskite quantum dots? I believe so, right?
Yes. I think for the quantum dots, for this type of quantum dots, we can tune in the composition as I showed in the slide, and by simply changing the composition and also changing the quantum dot size. It can be in, I think, in a very broad range.
I see. Thank you, Lian Zhou.
Yeah, I just follow the question. It's the perovskite, you can tune the composition and the size, and to get different band gap. And what are the benefit or disadvantage with tuning the size compared to tuning the composition?
Yeah, that's another good question. And if you tune the size, and the advantage is first I see the disadvantage. The disadvantage is if you tune the size of the quantum dots, and you have more challenge actually to stabilize, because actually there is certainly you need to use appropriate amount of surface ligand to stabilize, and normally the smaller and the surface energy is high, and you really need to have very good protection of the system. So that's one of the key challenge. And so, and in terms of the advantage, as if for some quantum dots, and particularly some composite, for example, you have mixed A side, mixed B side, and it's maybe not that easy and to tune the composition in certain range. But if you can have good control of the size, you can realize the same effect in terms of band gap and also the performance.
Okay, thank you. I have two questions from the other platform. So there's one question asking, are there any adverse effects of the oxygen vacancies for the PEC processes?
Can you say it again? Yeah.
Are there any adverse or negative effects related to oxygen vacancies for the PEC? I believe they meant for either the oxygen evolution reaction or for the water splitting process.
Yeah, okay, thanks. I think this is, again, another very important question. Of course, so oxygen vacancy sometimes is pretty difficult to control. And I would say, because actually, if it's on the surface or whether it's on in the bulk, during the reaction process, it can be not stable in some way. So, and you really need to have very good control of this approach. If you have too much oxygen vacancy, certainly you will damage the performance of the PEC system.
So I actually have a small follow-up question on this one. So, say you generate a material with the perfect density of oxygen vacancies, do you think the material surface will be stable throughout the process?
Yeah, that's yeah. I think this follow-up question is partially actually I answered. So it can be not stable, and in a way, so we really need to have a very good very good control of the whole system. But if we look at our PEC system, we also check the PEC performance over a period of time, and it's like Bismuth bandit, and it's the best performing one, and it's the performance is still pretty good in the long term. And in other systems like iron oxide system, it's pretty hard to stabilize the system. That's actually it's really dependent on upon the material system, and some intrinsic property of the photoelectrode materials can also affect the oxygen vacancy stability.
Great, thank you. There are two more questions here. One is fairly technical. It asks how to measure the diffusion length of the carriers I suppose it's in the material, maybe the oxides.
So all the diffusion length of the
carriers.
This one, I think we let's see. Just check the. Sorry, I think I need to just double check the details of.
Sure. Maybe yeah. I can move on to the next question here. The question asks about what is the step recombination or the catalytic rate? I guess it's maybe the turnover numbers or reaction rate of that.
Of the surface.
Right.
That's the surface reaction.
Right. I suppose so. Yes.
So this is related to which? Let's see.
I will guess it probably relates to the surface reaction that, let's say, maybe the OER or.
Yeah, this one. Yeah.
Are there any clarifications for this question?
Oh, so surface. I think the 10. You mean the turnaround number? Yeah. So is this related to the question? Or yeah.
I guess so. Yes.
Okay. So I think the surface reaction in here, and we can certainly use the TEFL plot actually to detect the reaction kinetics, and in this case.
Okay. Sounds good. I think maybe the slide is cut off at the bottom. That's possibly why.
Mm.
Okay. But yes.
Oh yes, that's the one. Yeah.
Right.
Yeah.
Okay. All right. So additional questions from the audience in the Zoom meeting room? No more. All right. Good. All right. So if no more, let's thank Professor Wang again for a wonderful talk. And also we would like to thank all the 4 speakers today for very stimulating and very diverse research talks. And we have heard from Professor Mintier on the really nascent research field on biocatalysis with bright future. And we also heard about exploration of entirely new classes of materials mixing for energy storage applications, and from Professor Wang on how you could modify and integrate existing material surface for performance enhancement, and also from Professor Min's talk that even the existing or established development and technologies can still use very fundamental research for further improvement. And the last but not least, I would like to thank all of the participants for this workshop. And I hope we all leave with something to think about our sustainable and green energy future. Shall we conclude the conference, Guiding, the workshop?
Yeah.
And our third session of the workshop starts at what time?
2 o'clock.
At 2 o'clock. So you can come at 2 o'clock for the last and guarantee a great session of the workshop. Okay. Thank you very much for participating.
Yeah. Thanks for the speakers and thank you for the audience. So I think all the talks are wonderful and they are very inspiring to the audience, especially graduate students. So welcome back at 2 o'clock in the afternoon for the last session of our workshop. Thank you again.
Thank you. Bye.
Bye.
Thank you.